Yeah, okay. Maybe we can start. So, good morning, good afternoon, and good evening, everyone. And thank you for joining across the globe. Welcome to the very first edition of Indus Symposium on Heliophysics Advancements that we are calling ISHA 2026. My name is Pratik Mank, and on behalf of entire organizing committee, it is my privilege to open this symposium. Let me briefly tell you the idea behind organizing this symposium. It was born from a very simple idea that PhDs, postdocs, early career researchers deserve a platform that is built for them, not one where they are an afterthought, rather a platform where the discussion is the priority, not the presentation of the slides. So, if you have ever been at a conference and held back a question because you thought it might be too bold or too basic or too challenging for the speaker, then this is the symposium. Here we want you to unleash, ask hard questions, challenge interpretations, and that's the culture that we want to foster through this symposium. The only rule is be respectful. Other than that, no question is off limits. And that said, before I walk you through the program and logistics, let me introduce someone with whom none of this would exist. That is Dr. Anshu Kumari Singh. Uh, she, along with her peers, founded Indus with the vision of building a collaborative community of heliophysics researchers. And ISHA is a natural evolution of the same vision, taking the community spirit and channeling it to a focused scientific symposium. So, with this, I invite Anshu Kumari to kind of say a few words about the journey of Indus and how it transformed to ISHA. So, Anshu.
Thanks, Pratik. Hi, everyone. Thank you to the Indus ISHA 2026 Organizing Committee for this invitation. It's a pleasure to be a part of this inaugural session and to reflect on the journey of Indus till now. I would also like to thank first all the Indus as well as ISHA participants who are joining us today for this ceremony, as well as will be presenting their work over the next 3 days to the community. So just to start, it has been almost 3 years since the idea of Indus was conceptualized. I see a lot of the early members with whom we started this group are here. And then later in July, it was launched. Indus began with a very simple idea with two simple motivations. First, to create a supportive environment or supportive system, especially for the early career researchers who often move institutes or many time continents. And the second idea was to have or to build a community where one could seek help, ask for support, share ideas, as Pratik has very rightly mentioned before, and to discuss science openly without the fear of being judged or without boundaries. So when we started Indus, we had a vision, but there were so many ideas we had to put hold on at that time because I had to leave within less than an year due to that early career cutoff we had fixed for Indus. However, I am very happy to see how even after I have left and the new coordinators and the new team has taken those ideas and such as be the podcast or be this Indus Isha symposium, which we had been talking about since the conceptualization of Indus. Indus began with a very small informal group of early careers, a very small group of early careers over WhatsApp. And then it was meant primarily for early career researchers to connect who are working in the field of solar and helio physics. Over the past 3 years, it has grown from a few members to a community of more than 300 early career researchers who are spread over the globe. And then I believe what makes Indus unique is it is built by the early career researchers and for the early career researchers. And that kind of reflects in everything Indus does, from be it the openness to discuss anything and be it the collaborative efforts. I have seen when I was there in the group and even later, if we have or if the early career researchers have any questions, queries, they usually open up to the Indus members and they ask it without any hesitation. So I'm very happy how this simple idea had evolved into this very insightful, big, meaningful network, which not only fosters scientific discussions, it also builds up on real collaborations. So looking ahead, I believe Indus will continue growing, and I think we are at some saturation point because I believe all the Indian early career researchers in the field of solar and heliophysics, or in fact space weather, are have now joined Indus, and there are more new researchers who are joining the field, are joining Indus as well. So I am very happy to see how it is shaping and how things are working for Indus, especially thanks to the new coordinators, Ketki and Pratik. And I'm not taking more names because I know there is a very, very big team of people who have been working towards the success of Indus. And I would like to thank all the members and contributors who had made this journey possible for the past 3 years. And with that, I believe Pratik will be giving more detailed information about Indus. So with that, I wish Isha 2026 a very successful and engaging session and meeting. Thank you.
Yeah. Thank you, Anshu. That was very quick and insightful. So now let me go through the Isha. So now we have some context of Indus, and let me give you the more information about the ISHA, which is the symposium that Indus is organizing. Okay, so ISHA is focused on, as I said, on PhDs, postdocs, early career researchers to provide accessible forum for them. And this is important because the number says so. As you can see, this database of Helio Index, 62% of our community belongs to this early career researcher tag. And that's why it is important to have a dedicated platform where they can discuss, talk, and be heard. That's why the special focus of this whole symposium is on discussions and like pondering on new things, debates, all those things. And we have kind of brought panel discussions and plenary talks with that in our mind. Obviously, panel discussions has the discussion word in it. Even the plenary talks are focused with the discussion in mind. So the idea is to promote in-depth scientific discussion and to bring mid and late career researchers as well as leading experts to have this discussion with the early career researchers. And this year's theme is space weather. We have multiple domains in heliophysics, and space weather is kind of a coupling of those domains. So I think it is very kind of interesting theme for discussions. Okay, so glad to share we have 237 participants who have registered for this symposium, and we have invited 15 speakers and panelists through 3 panel discussions focusing on career, science, as well as industry and agency. There are 3 invited talks on AI, SunPy, and future missions, as well as we have 6 scientific sessions, although they follow the traditional style, but we have separate slots for like in-depth discussions at the end of the session as well. So I would highly encourage to use it for good discussions. In total, we have 42 contributed oral presentations and 16 flash talks. And if you see this global context, this is the other locations where the participants are currently online or will be online during this 3-day symposium. There are in total 26 countries researchers participating in this, which I think is a quite diverse across the globe. This is a small infographic information about the career stage of the participants. Majority of them, 43%, are PhD researchers, then postdocs and master students, as well as 8% faculties have also registered. And thanks to them, they will be available in the discussions of panel discussions as well as invited talks. This is a schedule at a glance. There are 4 different phases each day, and we have a separate Zoom link for each day for all the 4 phases. And the highlight of every day where intensive discussions are expected to happen are the phase 4 in green, as you can see, which is panel discussion and invited talk. Obviously, don't expect much discussions or lack of discussions in other phases as well. I hope that people will be discussing a lot. But this phase 4 is specifically dedicated towards discussion. Keep an eye on the Google group. You will receive daily email uh, highlights from the organizers or session chairs. And you can scan this QR code if you haven't kind of added this events in your Google Calendar. So with this, you can easily add. You will find at the bottom left saying that add to your Google Calendar. All the sessions are open to all. Please feel free to join anytime, anywhere. And we would highly encourage to participate in the panel discussions and the talks, as I have been saying multiple times. I use chat in the Zoom without hesitation. Don't even think twice before saying anything. Just be respectful, but don't hesitate to say anything. If you want more attention, raise your hand. Somebody, maybe chair or the co-hosts, will like unmute you or let you drive this discussion. All the presentations will be made co-host so that they can easily present and improve the functionality. And at the end of this symposium, we will share a feedback form with you all, and we would highly appreciate if you can give us some remark how you felt during this symposium. And finally, some acknowledgement for the advisory committee and organizing committee. They have put very, very hard effort in organizing this and making it successful. So with this, thank you everyone for joining, and let's begin the first session. And yeah, let's see how it goes. Thank you. The first session is on solar interior. Let me unshare. Stop sharing. Okay, finally I found it. Yeah. I don't know. Have I stopped sharing now?
Yes.
Great. Okay. So Soumya, over to you. Thank you for sharing this session. So over to you.
We can't hear you, Soumya. Is it just me or?
No,
Yeah, I cannot hear Soumya Ranjan. Yeah.
Soumya Ranjan,
Okay.
not Soumya.
Soumya Ranjan. Yeah.
Yes.
Somo, can you hear us?
Yeah, I can hear. I can hear everyone. Is Soumya Ranjan not in the meeting? He should be.
Yeah. I just saw him right now
Ranjan is in
online.
the meeting. Yeah, but
Yeah.
maybe it's his audio settings. He is unmuted.
Yeah. Chiddeep, are we trying? Okay. Soumya Ranjan, we cannot hear you. Yeah, rejoin. Yes, please. Yeah. Uh, Thanks, Rohit, for coming on time. You are the first speaker, I think.
I did not spotlight my video. I don't know who spotlight me. Why is everyone seeing my screen?
Okay.
Okay, I just
That must
removed
be
the spotlight.
Soumya.
But yeah, of
Niranjan,
course, I'm very happy to be here.
yes. Yeah. No, still no. Is it any co-host permission that is required? Let me quickly check.
Pratik, by the time he figures it out, maybe we can go ahead with the first presentation.
Yeah, sure. Chitradeep, would you
You
like
can
to kind of?
maybe you can go ahead, please. Yeah.
Okay, okay, okay.
Can
Then,
someone hear me or still?
oh yeah,
Sure. Yeah. Sure.
yes,
It's
Oh,
back.
yes.
okay.
Why not?
Okay.
Cheers.
I don't know. Okay.
Okay.
I'm sorry for the glitch. I think I can share screens. Okay. Okay, so welcome everyone to the first session of, I'll not take much time. I'll just introduce the sessions and then how we are trying to do this. Almost most of the rules have been explained already. I'm Soumya Das, and I'll be chairing the session, the first scientific session of ISHA 2026. We have exciting talks lined up, and I encourage everyone to ask questions for the speakers. The time allocated for each talk is 12 minutes. I'll try and warn you at 10 minutes, and you'll have 2 minutes for discussions afterwards. And if we stick to schedule, then we will have even more time towards the end for extended discussions. And for the participants, I encourage everyone to ask questions. Please use the chat option or the raise hand option if you want to ask the question directly. And just a reminder that this session will be recorded. So if you are joining the session, then we assume that you are allowing us to be yourself in the recording. And I'll not take much time. With that, I'll unshare now, and I invite Dr. Rohit Chubba to share his screen, his presentation. He'll be discussing about von Karman Horvath similarity of spatial correlations and distribution of correlation lengths in solar photospheric turbulence. Rohit, please. Thank you.
Okay, can you see my PowerPoint presentation?
Yes.
All right. Yeah, thank you so much. It's a pleasure to be here. Very glad to join all of you for the first session of the symposium. I will be talking about photospheric turbulence, and in particular, some properties of the spatial correlations of turbulence in the photosphere, and this sort of mysterious thing that I have here, von Karman-Howard similarity, which I think most people would not be familiar with, but hopefully I'll leave you all with some sense of what it is, why it's important. Okay, let me start off by introducing the and motivating the study by saying that the solar plasma in general is regarded to be turbulent and highly dynamic in a very broad sense. Of course, the corona and solar wind is famously very turbulent, and the turbulence in the corona and the solar wind plays a significant role in heliospheric dynamics. Uh, Most of the turbulence that you see in the solar wind is sourced in the sun, comes from the photosphere. The basic picture is that you have uh, motions in the magnetic foot points of the solar wind on the photosphere. And these foot point motions are related to the convective motions that you have in the interior of the sun. But because of these motions, alpha waves get launched into the atmosphere where they can create turbulence and produce lots of interesting dynamics. Now, photospheric turbulence has not received as much attention as interplanetary turbulence, but there have been a bunch of studies looking at common turbulence phenomena like uh, diagnostics like spectra, diffusive motions of magnetic elements, and intermittency properties. But the thing I want to focus on today is the spatial autocorrelation function of the turbulence and the associated correlation length. So these correlation lengths are basically the characteristic spatial scales of the turbulence. Okay, so just to summarize the goals of this study, we want to use magnetogram observations from HMI to compute spatial autocorrelation functions of magnetic fluctuations in the photosphere. From these autocorrelation functions, we want to derive the correlation lengths, and we want to see if the correlation functions follow a universal form. And this is the von Karman-Howard similarity hypothesis that I'll talk more about. We are also interested in getting the probability distributions of the correlation length, lambda, and relate all of these results to what we know about turbulence in the corona and in the solar wind. Okay, so this is the HMI magnetogram that we used in the study. It's from 2010. To minimize projection effects, I only analyzed the disk center, which is shown in the plot on the right. So there's nothing unique or special about this magnetogram. I just picked it because it has both quiet sun regions and active sun regions, right? And it's from a low solar activity type of period. So some mathematical details. If you have a turbulent magnetic field, B, so this is one component of the magnetic field vector, then the single time 2-point autocorrelation function of this quantity is defined like this. So you have the magnetic field as at a position R, and it's multiplied by the magnetic field at a position which is displaced by this vector L relative to R, right? So you've got a lag between these two magnetic fields, and you compute the average value of this product over some suitable averaging domain, which is represented by these angle brackets. So this gives you the autocorrelation function for one lag L. And if you vary the lag L, then you get the ACF as a function of the lag. So the correlation length, which is associated with the largest turbulent structures in the system, sometimes called the energy containing structures, is defined as the integral of this correlation function with respect to lag, right? And in this, it's normalized by the zero lag value of the correlation function. So this von Karman and Howard self-preservation hypothesis or similarity decay hypothesis, it's a seminal result in hydrodynamic turbulence theory. It basically asserts that the correlation function can be expressed in this form, where B square is the average turbulent energy, and this script R is a universal function. And you'll see here that the argument of this function, the lag, is divided or normalized by the correlation length. So this hypothesis asserts that such a universal correlation function can exist for any turbulent flow. Okay, and this hypothesis provides a formal basis for some widely used turbulence modeling approaches, which are, for example, they're used in global solar wind simulations, like the Michigan Awesome model and the Usmanov et al. Model, and so on. Like any kind of global solar wind simulation in which you want to include turbulence effects, it uses some phenomenologies which are based on this von Karman and Howard similarity hypothesis. So to compute the autocorrelation functions from my magnetic field map, I divide this distribution into averaging subdomains as shown in schematic form here. I take my lags in the x direction, which roughly corresponds to longitude, and in the y direction, which roughly corresponds to solar latitude. And within these averaging domains, I compute my autocorrelation function. So because the mean field, magnetic field, is out of the plane of this map, and the lags are taken in the plane, what you get here is the transverse autocorrelation function, and therefore the transverse correlation lengths. So this is transverse to the mean magnetic field. So this shows you the results of this of the correlation function calculation, and the sequence of plots shows you how you go from this wide distribution of correlation lengths to the quasi-universal form that is hypothesized in that similarity hypothesis. So the top left plot shows correlation functions as a function of lag. Each curve here comes from one averaging domain from my previous slide. The blue curves come from quiet sun regions, and the orange curves come from active regions. Right, and you see this huge order of magnitude variation in the behavior of the correlation functions and the values. The first step in recovering this quasi-universal form is to normalize by the average energy within each averaging domain. This is actually equivalent to normalizing by the zero lag value of the correlation function, which is a very common step. But after you do this, this is what you get, the bottom left plot. So now each correlation function has a maximum value of 1. And you can see that there's a little bit of a reduced spread now, but you can still see that the active regions tend to decorrelate slower than the quiet sun regions in general, right? And the next step then is to take this R prime correlation function, and each the argument of this correlation function, the lags are normalized by the correlation length of each respective correlation function. And when you do that, then you get this, the gray sort of cloud of curves that you have here. So you see that all the curves have kind of collapsed onto this somewhat quasi-universal type of a form. And I've shown the average value of the correlation function in the dashed cyan curve over here, and a reference exponential decay function in the magenta curve. And you see that the average value lies very close to this exponential decay curve. Another way to look at this is in these box plots, where each green box contains 80% of the distribution. So the middle 80% of the distribution is within these green boxes, all again indicating a very nice collapse to this quasi-universal exponential decay. So the von Karman-Howard similarity hypothesis was actually verified for the space-time for the first time in space turbulence by my colleague Shoham Roy recently. And this work extends the validity of this hypothesis to the photosphere, which suggests that the photosphere is in an active turbulent state. We were also interested in the probability distributions of the correlation length, and it turns out that the PDF is well described as log normal, which means that the log of the correlation length follows a Gaussian distribution. And so a log normal distribution
Rohit, you have to
indicates...
open it.
Okay. This type of distribution indicates that you have multiplicative nonlinear processes at play. It's also observed in the correlation length of the solar wind turbulence. You see log normal distributions. And you can see from this that the average correlation length is around 1,500 kilometers, which is close to the scale of solar granulation. This plot shows a sort of map on the photosphere of the correlation length. The correlation length distribution on the right corresponds to the magnetic field distribution on the left. And you can see there's a large variability in space. The active regions can reach correlation lengths as high as 9,000 kilometers, much bigger than the quiet sun correlation lengths. And this is also hinting at a possible correlation between the magnetic field strength and lambda, right? Because active regions have larger magnetic field strength. And indeed, if you make a scatter plot of lambda with the magnetic field strength, and here this is the mean magnetic field strength, then you see this positive correlation. I've also fit some empirical functions to this distribution. And these can be useful because to compute the correlation length, you need high resolution magnetograms, right? But from these empirical fits, even with a low resolution magnetogram, where you just have the large scale magnetic field, you can estimate the correlation length values from such a magnetogram. And this can be useful to get, for example, boundary conditions for the correlation length from synoptic maps, which are widely used in solar wind modeling. So just in my last slide, just putting together a bunch of recent studies from all over the heliosphere, you can get a nice picture of how the correlation length evolves with distance from the sun. So the plot on the left is based on remote imaging observations. And you start off on the photosphere with a correlation length of around 1,500 kilometers. You increase it by the time you're at the base of the corona, you reached around 10,000 kilometers. And then from in situ observations, Parker Solar Probe, you see that there's a steady increase from, let's say, around 20,000 kilometers at 0.1 AU to around a million kilometers at 1 AU. So this type of distribution of correlation length is very important for energetic particle transport models because energetic particles get scattered by turbulence, and the scale of the particles which are scattered is determined by the correlation length of the turbulence. Right, so just summarizing, we used HMI magnetograms to characterize the correlation functions of photospheric magnetic fluctuations. We confirmed the von Karman-Howard similarity hypothesis, revealed the spatial variability of the correlation lengths and their probability distributions. The correlation scales tend to have log normal distributions. The quiet sun has a mean near 1,500 kilometers, close to granular scales, while active regions have systematically larger correlation lengths. We also noticed a strong correlation with the mean magnetic field for the correlation length. And in future work, we're hoping to look at temporal correlations, effects of solar activity, and more complex magnetic field data sets like vector magnetograms and maybe high resolution magnetograms from DKIST and Hinode. And this study was published last year in monthly notices where you can find more details on it. And that's it. Thank you.
Thank you, Rohit. I don't see any questions immediately. Okay, I have
I saw
one
something
question
in the
in the chat.
chat. Yeah.
Yes. So, Shivatosh, if you do you want to unmute or okay, but I'll read up the question now. What is the physical significance of the von Karman-Howard similarity hypothesis?
Right. So,
Um,
yes. So this physical significance really is that you can express the correlation function in terms of a very small number of characteristic scales, right? So if you know the correlation scale and if you know the average energy, then that sort of completely describes the spatial correlation behavior or the decorrelation behavior of the turbulence. So that's sort of the importance of this similarity hypothesis. And if you assume that the correlation function has this universal form, then you can derive a set of equations for the turbulence, which describe turbulent decay in a physically sensible way. So it's sort of an assumption based on which you can derive models of turbulence decay. So it's a big subject, but that's just like a basic sense of why it's important.
Thank you. In the sense of time, I see Ankush and Zubair, they have their hands raised, but we'll keep the questions towards the end. Rohit, if you can unshare your screen. Our next speaker of the session is Dr. Mohammed H. Talafa. I'm sorry if I'm pronouncing your name wrong, but he'll be discussing about modeling solar magnetic field evolution with physics-informed neural networks and WSO synoptic maps.
Okay. Can you hear me?
We can hear you,
Okay,
but your
and
presentation
my
is not up. We are seeing Chrome. Yes,
okay,
we can see your
so
presentation now.
I think everything is perfect.
It's in
Okay.
full screen, yes.
Okay, thank you very much for having me. Good morning, good evening, everyone. My name is Mohammed Talaf. I'm from the University of Sharjah. This work was in collaboration with the Indian Institute of Technology at Indore. And we actually, this is the second step of the work. The first step will be presented by Jito, the presentation after my presentation. But for now, I try to summarize what is this ongoing work that we are doing now currently. So basically, we try to model the solar magnetic field evolution using the physics-informed neural network, and also we use the WSO synaptic maps. So our motivation is that we need to know how will machine learning enhance our ability to predict the solar cycles, and if the physics-informed neural network can regenerate the solar surface magnetic field, including different nonlinearities, and what kind of observations we need to use in the PINN. So as we all know, we have the kinetic rotations, we have the synoptic maps, and this kind of synoptic maps that we get from the WSO, the Weather Solar Observatory, and we try to replot these the WSO synoptic maps with some interpolation, and to be able to use it in our work. So we collect all the synoptic maps for the recent 5 solar cycles for every month, and then we try to make one big synoptic map for each cycle. So this is, for example, for cycle 25, the current cycle, which is started in December to 2019 until today, or until the beginning of this work. And also the for 24, 23, 22, and 21 solar cycles. So basically what we did is that we collect the synoptic maps for every month in every year in every cycle, and then we group all these together, and we did some kind of interpolation to enhance these synoptic maps. And this is our base that we can use to make the neural network learn from these maps. So this is a few basic about the SFT, the model that we use, the surface flux transportation model. Basically, we solve the induction equation on the radial part, and we get the advection and diffusion terms. And in addition, there's 2 terms were added later, the decay term and the source term. So basically, we started from the source term, which is here is 2 opposite polarities active regions in both hemispheres, and then we make these evolve with respect to time, and finally we can look to the polar field by the end of the cycle. So this is our numerical solution. But what we are trying to do here, that we are going to use as a source. We are going to use these the big synoptic maps, each one for one cycle. So basically, this is also some basics about neural network. So we have input layers, we have hidden layers, and we have output layers. In each input, we have some weights, and each of these nodes, we multiply the weights, and we have some activation function, and then we have the output. And the special thing about neural network or the physics informed neural network that we, in the last layer, we do some automatic differentiation with respect to the input layer. So let's say in our model, we have the time and latitude, the magnetic field in time and latitude, and then we try to solve the magnetic field with respect to these two parameters, and finally we differentiate with respect to these two, and we try to adjust the weights based on this differentiation. So this is basically what the physics informed neural network. And to do so, we make a total loss function, which comes from the initial condition, the boundary condition, the data itself, and the PDE. So this is a kind of summary. I will not go in details. And these are the steps. So we have input layers, we have some hidden layers. We choose 8 layers with 32 neurons in each. And we have activation function. Typically, we use tan hyperbolic. Sometimes you can use Sigmund or ReLU activation function, but in this work we use the tan hyperbolic. In the output layer, we have single physical output, U of theta and T, which is the magnetic field, and we do the automatic differentiation, and then we do two stage optimization. We have the Adam optimizer, and we have the BFGS optimizer. So basically, these are the flow of the work. And this is from our first part of the work. This is already published in the Astrophysical Journal, and we were able to look for the dipole moment for different cycles and for different quenching mechanism. I will not go through the quenching mechanism. I think Jitho will explain these in details. But we were able to regenerate the dipole moment based on the numerical source function without any data. So this was based on the source function that I mentioned earlier, this one, and it was based basically an opposite polarity of two rings of magnetic field in each hemisphere. Okay. And so this is our source function. This is the numerical source function, and this is the solution without a neural network. This is like a numerical solution. Okay, so the first thing is that our result which was based on the source function. And you can see we already have the butterfly diagram. This is from the neural network after it learned how we can have the butterfly diagram. And in this solution, we missed the polar field. So we didn't have the polar field patches that reverse its polarity. So we are able to regenerate the butterfly diagram itself. And if we mix the source function solution with the WSO synoptic maps, also we started to see some inflows, let's say, or some flows toward the polar field, but still we can see that strong polar field patches. And also here you can see the dipole moment evolution. This was for 4 cycles. And if we rely only on the data, so our first try was a total miss. This is our first try. So this was based on several cycles, 21 to 25. And the neural network, let's say, failed to get even the butterfly diagram. We can see some the polar reversals between the patches, but we can see the butterfly diagram in its essence, and we can see the polar fields also. So it was a kind of failure. And our second try kind of we get things organized a little bit. We have the reversals. We have some patches, but for some reason we were able to solve it. We had polar feed at the beginning, and then it decay for some reason. But finally, we have for one cycle. This is for one cycle, okay? And finally, we were able to solve this problem, and we can see the
Alaf, we have 2 more
evolution.
minutes.
Okay, so I think I'm almost done. So we have the polar feed. I I try to be not that much technical, uh, and here we plot the absolute value of the magnetic field. This is was the reason behind this was to make an index number telling us how much our prediction was correct. Um, and these are my conclusion. Thank you for having me. I leave you with this. Thank you.
Thank you so much for sticking to the time. Um, I don't see any questions in the chat for your talk, but if there are some, I do have one question though.
Yes.
So I am, if I am interpreting this right, then all the loss functions and numerical models that you started with to train the network, those numerical terms, for example, the advection terms, where specifically the meridional flow, which is still not directly observed. There are many simplistic assumptions to the form and amplitude of the flux transport modeled meridional flows. How
Mm.
good they are or how much weight do they have in into your results? For example, the meridional flows are the drivers for the polar field buildup in most cases. So if your assumed parameter space for that particular term, if it
Mhm.
deviates from the observations, then how will that impact your final results?
Okay, so for let's say for the advection terms, the our trial were for one-dimensional SFT model. So basically, there is no differential rotation. We solve it in one dimension, and our meridian flow was a sinusoidal function. The amplitude was about 12 meter per second. However, the diffusion is a little bit larger. You may know that the diffusion is around 450 to 500 kilometers square per second. So we use this. So basically, we use a one-dimensional model at the beginning, and in later when we use it with a neural network, we use the two-dimensional model, but uh, we put the profile that I think Sandro Grass did it earlier, 2006 or something like that, which was a polynomial. Um, I don't remember the exact formula, but the amplitudes were in meter per second and kilometer square per second. I hope I answer your questions.
Okay, thanks. So we can again discuss in the discussion sessions. Thank you so
Yeah,
much.
yeah, okay. Thank you.
Our next speaker is Jitu. He'll be talking about investigating nonlinear quenching effects on polar field buildup in the sun using physics-informed neural networks. Jitu, I will remind you at 10 minutes. We'll have 2 more minutes, please. Thank you.
Yeah, yeah, I think you can hear
We
me.
can see your screen and hear you, but it's not in the full screen mode.
Yeah, okay. Yeah, so I think it's visible now.
Yes.
Okay, thanks. So, hi, I'm Jitu from Department of Astronomy, Astrophysics and Space Engineering in the Institute of Technology, Indore. First of all, I would like to thank Indus and the organizers for such a great opportunity and such a great project. And I hope that we would be able to see this like maybe year after year or something. Yeah. So today I will be talking about our work on investigating quenching effects, nonlinear quenching effects on polar field buildup using pins. So already Dr. Talafa has introduced or has talked a bit about what we have been doing or what we are currently trying to do. So this work is actually proceeding to that work that Talafa has already presented. Here we try to understand if we can use machine learning technique called pins to model different quenching mechanism, and if we can, then what all physics or what all understanding can we extract from such a study. That was the basic uh, thought when we started this work. Now, we all know that we are all from physics background, so we all know that the magnetic field is something that is very crucial for many sciences, either let it be space weather modeling, let it be understanding the magnetic field, polar field, or let it be understanding on how strong or weak the cycle are. Everywhere we need to know how and what are the different processes involved in the magnetic field evolution. So our aim is to work in the similar direction. And for this, we use something called SFT that Dr. Salaf has already described in detail. So the basic idea, just for completeness, is that we consider that the magnetic field on the solar surface is completely radial. And once we have a radial field, we see how these magnetic fields evolve or how these magnetic fields decay in different directions. For that, we have different physical methods, like we have the advection neuronal flow, or differential rotation, we have diffusion for supergranular motions, we have decay term to take care of all the magnetic field that is going radially outward, and we have the source term for taking care of all the active regions or magnetic field that is being dumped on the photosphere on the solar surface. Now, one important question in this basic equation is that we know a bit about Maudronian flow and differential location, so we can use it in some empirical fashion. We know a bit about differential rotation, diffusion, so we can use it. But one major problem in such a setting is to understand the source function. Now, one straightforward thing that we can do is to guess that you have linear SFT where you put in Gaussian fields onto the solar surface and see how those Gaussian positives and negatives in both the hemispheres evolve. Consider in a 1D, you will see how this, if you assume a Gaussian magnetic field, how these Gaussian magnetic fields will be moving towards the poles. This is first basic thing that we can do, and we have already tried this, and this is already published in APJ. Now, further extending, we wanted to try what are the different nonlinear things that could affect in such a system, and we kind of chose two nonlinear source things into the setting. One is tilt quenching and one is latitude quenching. So I would like to take a few seconds to explain what these two are. Tilt quenching basically means that, let's say you have a stronger magnetic field, a stronger magnetic flux rope. Because of the magnetic buoyancy, these flux ropes comes up, and because of the Coriolis force, it gets a turn and a tilt. Now, if the magnetic fields are stronger, the tilt will be, the buoyant forces will be much stronger, and you get a very less time to tilt the magnetic, the flux rope, and hence the angle with respect to the latitude angle, if you consider, will be very small. So for a stronger cycle, you will have a lesser tilt compared to a weaker cycle. This is called tilt quenching. And the second physics that we try to incorporate is the latitude quenching, which means that if you have a stronger cycle, then since initially in the cycle you will have more active regions, and towards the end of the cycle you will have lesser active regions. So the mean latitude of the total active the magnetic properties into the photosphere will be a bit higher. So active regions are like most of the active regions are towards a lesser away from the equator and closer to the poles, and this is called latitude quenching. So here, when we say quenching, it means that the strength of the cycle, strength of the magnetic flux ropes will affect what happens to the tilt and the emergence of the cycle. And what we try to understand is that can we kind of study about these physics using something called physics informed neural networks, which Dr. Talaf has already introduced. So what this setting is like in a normal neural network, you can see that You have inputs, you have outputs, they are connected with different layers, you have loss function and all. But usually we use data that we have, but in such a setting, we have less data or we don't have continuous data which is available. And also we have very noisy data. In such a case, what we can do is we can do something else, like if we know something more about the system. In this specific case, we know that there is a SFT equation, we know there is Maradona flow, there is diffusion, all this happening. So can we use this extra understanding or this extra knowledge that we have about the system to work with it? So we try to include these extra understandings into the training network so that these understandings can kind of hand in hand work with the data. So data and this understanding goes together and we can kind of learn what happens to the system. So we have used the pins network to solve the SFT setting that we have discussed earlier. Now, using this setting, what we did was we tried to simulate a lot of cycles. So we wanted to do something called a statistical study where we kind of do a lot of cycles. Mostly we have tried almost 1,500 cycles. So we have continuous 500 cycles. I have shown a few years in the plot. So you can see the alternating polar fields and everything. Now, with this setting, we tried to calculate the dipole moment because we were interested in calculating the what happens at the poles. So we tried to calculate the dipole moment. Dipole moment kind of tells you how strong or weak the polar fields are. With the dipole moment, we did something called deviation in dipole moment. Now, I would like to spend a few seconds here to explain what or why this deviation is what we are interested in. If we have a linear cycle, then we know that if the source increases, if the source is stronger, we will have a stronger cycle. And if the source is weaker, we will have a weaker cycle. Now, what this nonlinearity does is that it kind of bends this curve and it kind of reduces the total effect that we have. So if there is a larger tilt or a smaller tilt, the strength will actually decrease the effect because of some cancellations. And similarly, if we have more values in the latitude, the latitude quenching, that also does a similar effect. So what we did was we chose different SFT parameters. SFT has inset parameters for meridional flow, decay, diffusion, and everything. I have shown a set of parameters. This is just for one parameter. We have tried for a set of parameters, and we studied how for each cycle, how much dipole moment gain is happening, hence the deviation in dipole moment. So from this, we understand in each cycle, how much dipole moment has been increased into the system, injected into the system by such a source term, and then we change the physics for different quenching mechanisms also. So this is what we have done. Now we repeated it for a very different set of meridional flow and diffusion parameters, and we tried to connect it with something called the lambda Rx dipole range. So dipole range actually gives you the latitude until which you have the magnetic fields and the diffusion and the meridional flow as a kind of opposing effect, because meridional flow takes the parameters more, takes the magnetic field more towards the poles, helping in changing the dipole moment and giving a more polarity. But the diffusion kind of tries to diffuse things before reaching the poles. So it's kind of a tug of war between these two parameters. And we kind of model it using something called lambda R, which is the dipole range. Now, with this, we try to understand what different parameters can do. On the x-axis, you can see the meridional flow, and on the y-axis, you can see the deviation that is happening because of these things. So on the y-axis, you have the diffusion coefficient, and the color bar gives you the difference. Now you can see that there is a trend in both the latitude quenching case and in the common latitude quenching and tilt quenching case. So this shows that the parameters have something to do with the dipole value that has been chosen. So we try to see what this relation could be, and we identify that it has kind of a quadratic nature. We try to put all the lambda r's, and we find that it's kind of getting a quadratic nature. So it's like the parameters are related to the decay to the dipole gain in kind of a quadratic nature. So this is what we understand. This is something that has been identified numerically before by Talafa, and we were able to kind of reproduce the same thing with a pin setting and also to constrain it better. Now, what we ideally understand from such a setting, if you are looking on a linear SFT model or on a linear case, what happens is that the active regions get stronger and stronger, and you get a kind of exploding or a decaying cycle. But actually, what happens because of the quenching mechanism is that if you start with a stronger cycle, because of the strong cycle, we know that the latitudes, the magnetic fields will be towards the poles, closer to the poles, and there will be a lesser tilt. Because of this, there will be less cancellation across the poles, and the more active regions will close the
Jit, you have 2 more minutes.
yeah, sure, thanks. So towards the poles, and there will be changing of the polarities, but you will get a weaker cycle. Now, if you start with a weaker cycle, what happens is that the active regions are very close to the equator, so the leading polarities can go towards the poles, but the trailing polarities will cancel each other across the equator. If you can see my cursor, kind of like here. So only the leading polarities will go towards the poles. So a stronger magnetic field is going towards the poles. It will give you a stronger cycle. So it's kind of a strong weak setting that is happening. So you will get an alternating strong weak or an even odd cycle. That is what happens if you just take into account such a quenching mechanism. So quenching actually makes sure that this setting happens and sun does not go in a single direction of explosion or a second direction of complete non-active silence. So this kind of makes sure that the balance takes care. Quenching is actually can be considered as the reason for such a setting that is to happen. But if you see originally, if you see the data, it does not have actual this the strong and weak is not exactly alternating. This is mainly because here we have assumed that the Marine flow and all the safety parameters will be more or less constant, which is not exactly the case. So it could change with time also. So considering that this even out exact even out structure could be a bit suppressed. Now I will leave you with the summary and some conclusions. And the major limitation with such a study is that since we have did a statistical study for around 500 cycles, we have taken many empirical models into it to understand what the process is doing. So we have assumed different time profiles and everything, which could be one of the limitation. And the future work or the work that Tarek has already said, that we are looking into using original synoptic data so that instead of a kind of statistical case, can we look into original observations and see what happens? Can we kind of train the model with a setting, and can we kind of understand what is happening further? So thank you, and I'm open for any questions now or during the discussion session also.
Thank you, Chitu. Very nice talk. I have a couple of questions, but I'll keep the questions towards the end. I'll not ask the questions now. Let's keep the questions for discussion.
Okay.
Okay, so our next speaker of the session is Atul Bhatt, and he'll be presenting about apparent transverse motion of light bridges and their coupling with coronal loops.
Yeah. Hello. I hope I'm audible.
Yes.
Okay, great. Okay. So, hello everyone. Thanks to Indus for this wonderful opportunity to present our work. We have benefited a lot from all the initiatives of Indus, and I'd like to present my work in this opportunity. My work is primarily based on sunspots. So, my PhD thesis actually involves studying small-scale magnetic features around sunspots, and that has led me to this work. So to begin with, let me just briefly describe the light bridge quickly. So light bridges are basically long streams of plasma that you usually see around sunspots. It is usually surrounded by umbra on either side. So there has been studies that have told us that light bridges are formed usually when two sunspots coalesce or combine to form one sunspot or one umbra, and the plasma in between forms a light bridge. Or sometimes we see light bridges form into the umbra from like protrusion from the penumbra, and later the sunspots also split. So talking about various forms of light bridge, there have been certain studies that have described them as granular, where you have granular structures within light bridge like we see in the quiet sun, but smaller. We have light bridges with no granular structure, but some penumbral intensity in them. And there have been also some papers on light bridges described as streamers that are dots within the umbra, but they are slightly brighter than the umbral dots. So there have been a lot of studies on light bridges, and they have also been associated with the higher atmosphere. Although light bridges are mostly associated as the photospheric feature, we do have observations of the light bridges in the chromosphere, and also some correlation with coronal loops, where formation of light bridges have shown some correlation with the coronal loops around the sunspots. So my work mostly is on this active region, the active region 13590, which appeared in February of 2024. And as I mentioned, my PhD thesis is basically to study the magnetic features around sunspots. So I was looking for certain light bridges, and I found this one to be very interesting. Here are the basic details. I'll quickly move forward. When I observe the sunspot, what we see in the normal intensity here in the video I've shown is basically you have this light bridge here within the umbra. And what you see here is it's forming this curvature like of structure. So as the light bridge evolves, the light bridge protrudes from the penumbra, enters the umbra, but then after a while, it is apparently moving like it's in a horizontal or transverse motion. So that caught the eye, and that was the motivation for this work. And then we studied this light bridge through various analysis. And one of the first things I did was to observe the light bridge at contrast enhanced versions. So what you see here is the light bridge appears to be a single straight light bridge here. But at the same timestamp, if I move forward in the contrast enhanced version, you will see that the light bridge actually has an extended tail. So we have a main arm like the light bridge that is visible in normal intensity here, which is very bright in this image here. And we have an extended tail, which is very, very, very faint. And that is what motivated us to study this further, because light bridges are known to be protrusions into the magnetic flux tubes. And we have the Parker Solar model, which says that within the umbra, you have a bunch of magnetic flux tubes tightly packed. And light bridges are usually plasma that protrudes into these tubes. But then this plasma there cannot really push through these magnetic flux tubes, is what is believed. So for a light bridge to push through this magnetic flux tube, there must be something else going on. And that is what caught our eye. And then we proceed further with this work. And then as we usually do with light bridges, we study the magnetic properties. And conventionally, light bridges are known to have lower magnetic fields across them. And the inclinations are believed to be slightly lower. But in this particular case, we see that when the light bridge initially starts, as I see here, we plotted a line segment and the magnetic properties along that line as it cuts through the light bridge. The properties are very much similar to the conventional light bridges here. We see in the lower row here, the image, the plot on the left shows that the magnetic field drops, and then we have next to it the vertical magnetic field, which is also showing as a drop. We do have certain horizontal magnetic fields showing slight rise across the light bridge, and above that we have the inclination, which is also rising, and that is a conventional idea of a light bridge as well. So at this point we thought it was a normal light bridge, but then we studied the same light bridge a while later. I've enhanced the contrast here to show you the tail as well. The line segment which cuts through both the arm, which is the bright light bridge I explained in the previous slide, and the tail, we see that the magnetic field in the lower images you can see on the left, the magnetic field drops across the main light bridge here. We'll call it the arm for the rest of this presentation. And then across the smaller tail of the light bridge, we can see that the magnetic field increases. We have marked the intensities using these red dots to help us identify where the light bridge begins. So we have the magnetic field dropping across the main arm of the light bridge, but it's increasing across the thinner tail, fainter tail. And again, with the vertical magnetic field, we see the same pattern here. It decreases across the light bridge, but increases across the tail. And the inclination in this case is not that of a conventional light bridge, because we see that the inclination drops across these two light bridges, as if the magnetic field is slightly going off from the line of sight. So with these magnetic properties, we were studying the light bridge, but then we realized the same sunspot on the previous day, on the 22nd of February, we have another light bridge that forms. So we have a sequence of images here. On the top, you'll see the normal intensity that we usually see a sunspot with. And then at the bottom, we have the contrast enhanced intensity. And on around 12 on 22nd, you see two light bridges from two sides, opposite sides of the umbral edge, protrude into the sunspot. And these are two different sunspots, as you see in frame F over here. It's also visible in the normal intensity here. But as you go further in time, it disappears in the normal intensity. But in the lower frames, you will see that the two light bridges combine to form one single light bridge. And then in the third frame, you'll see around 1936, it has a slight transverse motion as if something is pushing this light bridge. As you mentioned, the light bridges cannot themselves push through the magnetic flux tubes. So later on at 20 to 12, we see that the light bridge forms a very peculiar omega shape, and that is why we call this the omega light bridge. As just like in the previous case, we saw the tail of the light bridge form the S shape here. So we have the S light bridge here, and then we have the omega light bridge within the same sunspot. So moving further, analysis into the photosphere, we studied Dopplergrams. We corrected these Dopplergrams using the Quietson mean. And then we noticed that as these light bridges evolve, we do have counter-Evershed flows observed. And what was interesting was that these counter-Evershed flow appeared exactly at the umbra-penumbra boundary where the light bridges protruded into the umbra. So you can see the set of plots on the right here are from the S light bridge. You can see in the top frame a very bright red counter-Evershed flow here, whereas in the last frame you have a very bright counter-Evershed flow in the form of blue here. And again, in the set of frames on the left, you see the omega light bridge frames. And again, here in the last frame and the previous to that, you can see counter-Evershed flows. These are upflows, and then again, in the second frame here, we don't see exactly a downflow here, but we do see that the upflow is reduced, which may be because of projection effect is what we are seeing here. So counter-Evershed flows are usually associated with light bridges. So that led us to believe that these are maybe general light bridges, but then these light bridges do not break the umbra, they just disappear midway. So that is what led us further into seeing if these light bridges have any signatures in the chromosphere. So when we observed in the chromosphere, again, the set of plots on the right are the S light bridge. We have plotted them at two different timestamps. One is without the tail, which is the column on the left in the right image here, which I'm pointing to. And then the set of frames on the right side is when the tail is actually present. You can see in the top contrast enhanced frames that the tail of the light bridge is present. So when the tail is present, we look for the signatures in the chromospheric heights, and we see that the arm of the light bridge do have some signatures in AIA 1700 and 1600 images, but the tail is completely missing. And the similar case with the omega light bridge in the set of plots on the left here, you see that the light bridge omega shape is very much visible in the contrast enhanced frame, but in the AIA frames, it's not there. So this led us to believe that maybe these light bridges do not have any signatures in the chromospheric height and they are limited to the photospheric heights only. But then later, when we are looking at the general atmosphere across this timestamp when the light bridge forms, we notice in AIA 1700, large coronal loops form as the light bridge forms. What you have here is a set of frames that I've shown, ranging from the early hours of 23rd February till the late hours. And on the top four frames, you see that these are the timestamps around which the arm of the light bridge, where the first protrusion was observed. And between these dashed lines, you can see a very faint in frame B, a very faint coronal loop forming, which gets brighter later in frame C, and then it completely disappears in frame D. This is the time when the light bridge arm protrudes into the umbra. And later, around
Still we have 2 more
1448,
minutes.
yes, thank you. Later at 1448, we see another coronal loop exactly at the same point appear and then disappear. So the light bridge evolution has some correlation with the coronal loops. We can see here in these images, again for the S light bridge, as the coronal loop forms here in the first frame A and the second frame B, we see a gap appear between the coronal loops. And as the light bridge evolves, we see these coronal loops are split into two. And then smaller coronal loops appear when the light bridge also evolves over time. So quickly moving forward, we plotted a space-time plot for the coronal loop with artificial slits, and we notice exactly at these times that we have brightening in the chromospheric heights. And in the lower plots, you can see here as the S structure forms, when 3 points are intersected by the slit, we see this bright loop appear between 1448 and 1932, and there is some transverse motion as well. We follow the same method for the omega light bridge, and here we see that across the slit in the coronal loop foot point, the width of the coronal loop foot point increases as the omega light bridge appears, as the 2 points you can see here through the slit. So in both the cases, coronal loops kind of influence the light bridge evolution, and then we proceeded further to identify umbral core regions. And when we studied how they evolve over time, we see here in the top plots, region 2 and 3, they kind have a counterclockwise motion. And then when we studied the displacement, we found that the umbral core regions do have a displacement of 0.085 kilometers per second and 0.2 kilometers per second. So initial and final positions are marked. And in case of the omega light bridge, we see that the umbral core region here, 1, extends transverse to the light bridge, and it grows by about 2 megameters. So all in all, when we study these, we find some of the properties of our light bridge similar to umbral filaments and sunspot scars, which have been studied before. And we see that counter Evershed flows are also present within these. So maybe these light bridges are like cracks within the umbra, such that the plasma flow into these cracks appear as counter Evershed flows. And the raised inclination and appearance of coronal loop foot point right next to the light bridge are very similar to umbral filaments and sunspot scars. And the uh, signatures disappearing from the chromospheric height suggests that these light bridges are very much into the umbra, or maybe slightly maybe at a lower height, because it's very faint in HMI images. So we have studies which says that reconnection events in a near a sunspot lead to the reconfiguration of the flux tubes, which kind of makes the flux tubes move in a lateral direction. So that may be explained how these coronal loops were moving around and causing this light bridge to have an apparent horizontal or transverse motion. And we do know that this sunspot was one of the most flaring sunspot of that year, early that year. So we do observe light bridges generally, but in this particular case, we see that the light bridge has a very strong correlation with the coronal loops. Its entire evolution is kind of driven by these coronal loops, and these may be majorly because these are umbral core regions that are reconfiguring themselves, and an umbral crack between these umbral core region is kind of morphing into this shape that we observe as the light bridge. Thank you.
Thank you, Atul. I do have a question in the chat. So the
Yes.
question says, what could be the reason for the decrease in the magnetic field that you showed in the plots?
Yes. So we
If you
we
can be
know.
quick, it would be nice.
Yes. We know that the magnetic field across light bridges are actually lower. So if these are umbral cracks, then between these cracks, the magnetic field would have slight of spacing, and that may be the reason we believe is the decrease in the magnetic field across these light bridges in the umbral cracks.
Okay, thank you. Our next speaker is, our final speaker of the session is Suprabha Mukhopadhyay. He'll be discussing about solar inertial modes, effects of radiative interior. Suprabha, we can see your screen and I can hear you now.
Okay. So, hi, I'm Prabhu. I'm doing my PhD at MPI in Göttingen. Unlike the other talks, I will be going deep into the solar interior directly to the radiative zone and discuss the helioseismic aspects of solar inertial modes. So helioseismology has been uh, previously done using the pressure modes or P modes, which are essentially sound waves which are trapped inside the solar interior. And because they travel deep into the solar interior, they have been used to infer properties of the solar interior like differential rotation, meridional circulation, and so on, which are essential for dynamo models as we discussed previously in this session. But these sound waves are not very sensitive to many quantities in the solar interior, like the subsurface magnetic fields, the viscosity, and the order of convective instability in the convection zone. Recently, some other sets of waves have been observed on the solar surface flows. They are the inertial modes, which are restored by the Coriolis force. And since Coriolis force plays an important role in restoring these modes. They have a time period of the order of the rotation period of the sun, and they are global scale oscillations observed on the surface flows. And various studies have revealed that these oscillations play a both diagnostic as well as dynamical roles in the solar interior, and they can complement the P mode helioseismology. But before they can be used for helioseismology, the model for them, which we use as a linear model, it must be as realistic as possible. But it should also be as simple as possible, but not simpler, so that we can easily model these modes and compare with the observations to infer the properties of the solar interior. And to do that, we need to validate each simplifying assumptions which we make when we model these inertial modes of the sun. And one such example is that the validation of the simplifying assumptions in the continuity equation. I would not go into the details of the work, but present it as an example of such a validation which was published last year. For today's talk, I shall mainly restrict to the validation of the inclusion of the radiative interior. The previous studies, which modeled the inertial modes in a linear setup, only used the convection zone, which is shaded in green over here. So we try to understand, can we exclude the radiative zone when we model the inertial modes of the sun or not? And before we do that, let's just briefly remind ourselves what are the differences in the radiative zone as compared to the convection zone. Firstly, the radiative zone is very convectively stable or subadiabatic in nature as compared to the convection zone. And in between we have a transition region which is also stable, but the motions in the convection zone can penetrate into this transition region, and which also overlaps with the tachocline. And previously, Catherine Bloom and colleagues in 2024 have presented a nonlinear simulation in which they show that there exist Rossby modes in the convection zone and the radiative zone, and they might be in a separate wave cavity. However, we do not have the flow structures associated with these modes, as also how the modes in the convection zone and the radiative zone can be coupled with each other. So, to understand how the radiative zone affects the solar inertial modes, we model the solar inertial modes in two setups. In a setup which only includes the convection zone, and another setup which includes a significant portion of the radiative zone. And we quantitatively compare the eigenmodes obtained in the two setups. And here we find that the surface flows associated with them are very correlated with in the two setups. Therefore, for surface observations, we can use the convection zone only model to interpret these inertial modes. However, if we look deep inside, if we look at the RMS velocity, the radial profile of the RMS velocity, we can see that there are deviations near the base of the convection zone. And this is because of the penetration of the flows into the transition region, which is shaded in gray over here. This causes a deviation and changes the structures of the mode slightly, and which also affects the frequencies of the modes, which are shown here slightly, but the changes in the frequencies are not that significant. They are only a few nanohertz different, which is less than 10%. And therefore, the convection zone only model still remains valid, and we can use it for interpreting the observations. And we can use the radiative zone model when we require very precise frequencies as well as eigenfunctions for comparing with the observations. So till now we discussed only the modes in the convection zone. So how about the modes in the radiative zone? Because the radiative zone is also rotating and it also has a Coriolis force, so it will have these inertial modes in them. But the radiative zone is rotating at a rate which is different from that in the convection zone. That is why they are shifted in frequency. The frequency is on the x-axis over here. So these are the radiative zone modes. They have a shift in frequency as compared to the mode in the convection zone. And we find that these modes are slightly perturbed by entropy or bouncy, which changes the force balance in the modes slightly and has some different features as compared to that in the convection zone. We discussed the two types of modes, one in the convection zone and another in the radiative zone. But can they form global modes which have flow structures in both the convection zone and the radiative zone? We find that it is possible under certain conditions, which we shall discuss in the next slide. But here let us see some examples when such coupling can occur. So these are two of such modes which have flow structures both in the convection zone and the radiative zone. And here is a corresponding mode obtained in the same setup which has predominant motions only in the convection zone. And we compare these two modes which have very similar structures in the convection zone. And again, for both the modes, the surface behavior is very similar and correlated with each other. Also, the radial behavior are very similar, except in the radiative zone because one of the mode is evanescent in the radiative zone and another has Rossby mode structure in the radiative zone. So now coming to the condition under which such coupling can occur between the modes in the convection zone and the modes in the radiative zone. So there are two conditions. One is that the frequencies of these modes should match, and the second is that the symmetry of the modes should match. So here we show the modes with north-south symmetric vorticity on the left and the north-south antisymmetric vorticity on the right. The colored lines denote the modes in the convection zone and the gray lines denote the modes in the radiative interior. And we have marked these modes which can couple by the open black lines. So here we can see that only a certain fraction of the modes can be coupled with the radiative interior because of the dispersion relations of these modes. And this is when such coupling occurs. Now to
Okay, we
compare
have
with
2 minutes.
yeah. Now to compare with the observed frequencies, here we plot the observed frequencies of all the different types of inertial modes which have been seen on the solar surface flows. And we see quite a lot of them have frequencies close to the Rossby modes in the radiative interior. And such modes are shown in a translucent fill over in these plots for the two different symmetries. Now, to summarize the main messages from my talk, we found that the inertial modes in the convection zone are only weakly affected when the radiative zone is included. And there are Rossby modes in the radiative interior whose frequencies are shifted because the radiative zone is rotating at a different rotation rate as compared to that in the convection zone. And the Rossby modes in the radiative zone couples with the inertial modes in the convection zone under the conditions which we found in our work. And such coupled modes can help us get information about the deep radiative interior if we can identify them, but identifying them will be challenging because their flow structures are very similar to the modes which are not coupled, at least on the surface, as well as a little bit down, and also their frequencies are very close. And finally, the Rossby modes in the radiative zone and these coupled modes could also play dynamical roles in the sun by generating small scale dynamo effects in the radiative interior and also causing dissipation in the radiative interior. That's all for my talk. Thank you for your attention.
Thank you, Supro. Very nice talk. I do not see any questions specifically for your talk right now in the chat, or I don't see any hands raised. So let's go to discussing the whole session. It was really nice sharing a lot about very diverse topics, which combines a lot of things. I'll just, Chitradev helped me summarize all the questions into one document. I'll just share the document now, and then we can maybe just go ahead with the discussions. If there are any questions in between, if I see any hands raised, I'll ask them to unmute. Since we have already moved beyond a little bit our time, allocated time, we'll keep this short and try and see if how many questions we can address in this. So yes, so Chitradev had a question. For a very weak field, the correlation length scale drops more rapidly. And if he's correct in interpreting it, does it have anything to do with the nonlinear Lorentz feedback? It's a diminished feedback by the field on the flow. It's a question for Rohit.
Well, as I said in the chat, I think there's a log-log scale on the plot, so I have to see if it actually drops more rapidly for the weak field. But I think the relationship of the correlation length with the magnetic field was also a very nice comment by Dibyendu. I think it's a bit of a puzzle, this positive correlation between lambda and the large-scale magnetic field, because the correlation length is really sort of the driving scale of the turbulence, right? So if in your cup of coffee you put sugar and your spoon is stirring the coffee, so the scale of your spoon's motion is the correlation scale. And I'm not aware of any such correlation between the convective motions and the strength of the magnetic field that emerges, right? So why is the correlation length large when the magnetic field is large? There's one part of it which I think makes some sense, and that is that in the active regions, the correlation length is large. And to me, that makes sense because the active regions are more coherent, large-scale structures than the quiet sun magnetic elements, right? So in as far as like the quiet sun having a small correlation length and active regions having a larger scale, I think that probably is not surprising. But in the quiet sun, the fact that there seems to be a correlation, to me, it's a bit of a puzzle. In situ observations in the solar wind, I don't believe we see such a correlation between lambda and the magnetic field at 1 AU, let's say. So something to explore more.
Okay. Thanks, Rohit.
Of course. Do you want me to continue with Zubair, or am I talking too much?
Maybe one more question for
Okay.
Zubair's question. Yeah. So yeah, he had a question regarding increase in correlation scale from the photosphere to 1 AU. Do you think this is primarily due to intrinsic turbulence evolution, or is it more towards geometric expansion playing a dominant role?
I think it's difficult to disentangle the two. Because if you treat the correlation length as just a characteristic flux tube diameter, then that increases with distance, right? And the radial trend in the correlation length you get in that approximation isn't that different from the correlation length you get in the observations. Um, so I think, especially in the transverse correlation length, where you're looking at the correlation length transverse to the magnetic field, it possibly is heavily affected by the expansion. Um, I think in your previous remark, sure, there are all these different driving scales, but I think the flux emergence scale is possibly connected to the active region scale, right? And so the fact that I get a larger correlation length in active regions is suggesting that I'm measuring the flux emergence scale in that. So the variability in the correlation length I get might be pointing to these multiple driving phenomena.
Thank you, Rohit.
Thank you.
Of course.
There are a few questions for Dr. Talafa. I think he had answered some of these in the chat itself. But if there are any more questions, people can unmute and then ask. Although I had one question for him. For example, as you were mentioning, you are working with a one-dimensional flux transport model where the major driving advection term is due to the Merdinal flows. And Merdinal flow can have different profiles and can have different parameter space. And my question that time was, if how sensitive is the neural network to the variation in choosing a particular profile for the Merdinal flow in your model?
Okay. Okay. Now I got your question. Sorry, I didn't get it earlier. I think we didn't test different profile for the meridian flow. However, we used the profile, the sinusoidal profile that was based on the optimization earlier in 2019. We did optimization. We tested 5 profiles, and the best solution was, or the best profile was a simple sinusoidal profile. That's why we use it in the neural network. But we didn't test the sensitivity of other profiles to the neural network. So maybe it will be a good idea to test it with the configuration, the PINN configuration.
Yeah, thank you.
Thank you.
Jitu, you have a bunch of questions from Chitradev. It might be not too much relevant for SFT. I think it is. But does the combination of SFT plus PIN have a potential to come up with any additional insights in explaining the onset to and recovery from the grand minimum like epochs, like subcritical dynamo state? Yes.
Yeah. So thanks, Chitradeep. So I think such a setting should be able to do it. Even though we haven't tested. So I think the prominent contribution in such a setting should come from the different profiles, as just discussed before, different Merdinal profiles that are existing, as well as different values that are existing. Because ideally we don't use the like any observational setting directly, but we use empirical settings. So if we kind of relate it to the observations that we have at that time, and then I think we should be able to do such a simulation. Yes, so I think it should be possible, but with the observations of that time, like the minima time, it should be possible, and it should give us better idea. But yes, we haven't tried it in that direction.
Yeah,
Kind of
thanks, Jitu.
transitions into
And yeah,
Devendu's
sure.
comment. Yeah, like the nonlinearity in these models can come from different processes that's playing in the flux transport process. For example, there can be inflows which have
Yes.
been found by different authors
Yes.
in towards the inflow towards the activation belts. Is there any insight from your?
Yeah, so it is actually true that inflows do alter this, like inflows is also a third non-linearity that has to be included into such a simulation. So in the numerical setting, we have like Dr. Talafa has already have the numerical setting where they have even published a paper with numerical inflows into the active regions as a part of the nonlinearity. But just in this work, we haven't tried that. We were just looking into two different two Kenji mechanisms. That's all. So, but there are works where such simulations are done with a numerical setting. But yes, with pins, we have never tried that.
Sorry, I might add some comments.
Yes.
So if we consider the three nonlinearities, the tilt quenching, latitude quenching, and the inflows in the normal numerical SFT solutions, usually we will have oversaturation of the magnetic field. So we have to make kind of a balance between all the three. Also, there's one argument about the inflows that it's the process actually what caused the tilt quenching. So it's still we still argue that okay, maybe it's separate quenching mechanism, but it might be deeply linked to the tilt quenching. So we are not sure if we can consider it as nonlinearity or not, but sorry, we can consider it as nonlinearity, but we are not sure if we can consider it within this model. So it will, because we saw that it will oversaturate the magnetic field. So this is just in short. Thank you.
Thank you. Atul, I think you have addressed this question, but I had one more question for you regarding light bridges. I think you are only working with mostly SDO data sets. Is it possible if you can, if you have access to highly resolved data from, for example, DKIST, where you have very nice spectropolarimetry and you can probe different layers, different optical depths, and can that help your explanation of the increase or decrease in the magnetic fields due to the underlying flows?
Yes, like I showed in the plots, the magnetic field actually increased in the faint tail. So that we believe is because of the resolution of SDO. And then we have been trying to get observations on DKIST. I've got some observations from Gregor, and we are working on the spectropolarimetry part of it to deduce the magnetic field region for highly resolved features like this and find out if such a thing can be supporting.
Thank you so much. If others have any questions, please feel free to ask. I didn't see any, so by the time I was compiling this document, I downloaded this PDF. I didn't have any questions for Suprabhu, but if you have any questions for Suprabhu, please feel free to ask or raise a hand. Let me check if there are any in the chat right now. Okay. So there was a question for Suprabhu from Chitra Diblain comment on the reliability of estimation of the modal power, given that the sensitivity kernels weaken rapidly as we go deeper into the convection zone and the radiative interior. I think the questions are already addressed. Okay, so I don't see any more questions right now in the chat. I have one more final question for Rohit. Since the correlation length scales are explored in the photosphere, is there a plan to do a similar kind of analysis in the chromosphere, where you can get the data from? I believe you can get these kind of magnetograms in a small field of view from DKIST, like VBI or WISP instruments.
I would be very interested in getting my hands on DKIST data just in general. Because the higher resolutions it'll be interesting to compare what the higher resolutions give, right? I think the chromospheric values have been estimated from eclipse image analysis, not as direct analysis as the magnetic field magnetograms, but they seem to show a consistent trend that you get a gradual increase of the correlation length as you go up from the photosphere, And then across the transition region, there's a rapid increase to the base of the corona. So in the solar limb, we have some estimates of the correlation length in the chromosphere. If there's decreased magnetograms for the chromosphere, then it'll be very interesting. Yeah. But I am not that familiar with the decreased data set. I don't know if they have a public magnetic field data product out yet.
So the data products has to be like you. It depends on the user. You probably have to connect with the people who are working on the
Right.
data sets. But there are full spectropolarimetric data sets available at different optical depths. So in principle, you can probe the chromosphere. Like you have the full IQUV vectors, and you can construct your own magnetogram at different heights. So that may help.
It definitely would be very
in this study.
interesting.
Yeah. Yes, I don't see any other questions. Maybe one more question, one final question for Jitu. Since you mentioned in one of your slides that diffusion is one of diffusion and advection, they are both are kind of working against each other in final buildup of the polar field. Since diffusion, okay, so the diffusion coefficient is one of the parameters which vary a lot in the parameter space. And there are no direct observations to support that these kind of diffusions are there, or maybe, I mean, the values can change depending on if you want to calibrate your model to a certain um, output, then you can tune in your diffusion value, diffusivity value, or the marginal flow profile and values. So, and there is another class of receptive modeling, which is advection dominated, which is like the AFT, advective flux transport.
Yes.
How the situation will be, how different would that be in a pin framework?
Yeah. So what advantage that we have with the pin framework that we have identified is that the flux calculations are better compared to a numerical setting. That is, the flux conservation is better. That is something that we have identified before. So it's more like that. It's more like in a numerical setting, what happens is that there is a second order flux diffusion that is happening, a numerical diffusion that is happening. So main advantage with the pin setting is that we can reduce this extra flux losses that are happening in the domain because of the numerical setting. Now, said this, as you rightly said, that the diffusion parameters are not well constrained. And in the setting like in AFT and all, where we don't use a single flow speed, but we have like flow speeds for like velocity fields are used as this thing. So I think that using an AFT kind of setting will help in kind of modeling it better in at least that kind of a setting, because it's more observationally constrained. But I'm not sure how much in a statistical sense it would help, because we are looking into a total picture rather than what's happening in in minor scales. So I think I'm very doubtful what would like total advantage would not be much. I think that's what I think, but yeah, it's not tested, so I think I would say that's my hunch.
Okay. More studies in the future may help.
Yeah.
Thank you, everyone, all the speakers of the session for very nice presentation and discussions. And if there are no more announcements from the organizers, then probably we should end the session.
The next, yes, let's
Yes.
move to next session. Thank you, Samiranjan. Nice session, very exciting. Let's shift to next one. Sargam is the chair. Request Sargam to chair.
Hello everyone, welcome to this session on this solar atmosphere. My name is Dr. Sarkambule. I'm a postdoc at University of Glasgow, UK. I work with Professor Lindsay Fletcher, and my research focuses on solar flare observation and radon simulation. So I'll be chairing this session. The session includes 6 presentations followed by summary session and additional question and answer. So we have exciting lineup speakers today. Each speaker is allotted 10 minutes for their presentation, followed by 2 minutes of question and answer. I request all the participants to use the chat box to share your comments and questions. Also, please include the name of the speaker you would like to address your question to. So our first speaker is Nancy Narang. She is a postdoc at the Royal Observatory, Belgium. Her research is focused on campfires. Campfires are the extreme ultraviolet brightenings identified by Solar Orbiter, and today she will be speaking about the on the magnetic origin of this fine-scale EUV brightening. So Nancy, you have 10 minutes for your presentation, and I will provide you 1 minute warning.
Okay, thanks, Sargam, for the nice introduction. So I think you can all see my screen well and hear me well. Sargam, if you just confirm.
Yes.
Okay.
Please go ahead.
I'm Nancy Narang from Royal Observatory of Belgium, and this work, what I'm presenting today, I'm working with EUI team and also with the support of FEE team. So today I will be talking about magnetic origin of fine-scale EUV brightenings in the solar atmosphere. And just to make the title more understandable, that specifically I will be talking about spatiotemporal property of these fine-scale EUV brightenings and their interlinks with the photospheric magnetic field. So what are these small-scale EUV brightenings, particularly observed by Extreme Ultraviolet Imager, that is EUI, onboard solar orbiter? So they were first reported to be observed by Bergmans et al. In the high-resolution imager telescope of EUI, observing in EUV passband. And here you see this set of observations which these authors used to first report the presence of such small scale brightenings in the solar atmosphere. And these observations were very unique and special in the terms because they were one of the first observations obtained by EUI onboard solar orbiter. So at this time when these observations were taken, solar orbiter was at almost at 0.5 AU from Sun, and this gave the pixel resolution of high resolution imager observations to be around 200 kilometers. And the cadence of these observations were 5 seconds. And just to emphasize what kind of small scale we are talking here, here you see one example of HRIUV observation zoomed in, and this square box. And inside this square box, you see a tiny dot, which is the HRIUV brightenings, a type of HRIUV brightenings that we are talking about. And if you zoom in here, you see a very distinct, very fine scale brightening in EUV passband. And then further, these authors compared the presence of these HRI-UV brightenings in AIA observations as shown here, and they could find the presence of brightenings in the vicinity of the brightenings observed in HRI-UV. But in most of the channels of AIA, these brightenings were not as distinct as in HRI UV. They had a fuzzy cloud-like appearance in AIA channels just because AIA has a coarser resolution as compared to HRI UV. So further, these authors performed statistical study of these small-scale EUV brightenings observed by HRI along with AIA observations. So they studied almost more than 1,000 events and found the occurrence rate of these events to be almost 200 events per second happening on the full solar globe, if assuming whole of the full solar globe is quite sun. And again, and their area and lifetimes were limited by the specific set of observation that they were using. And by using AIA observations and using DEM, the authors could estimate the approximate temperature of these brightenings to be around 1 million Kelvin. And thus, these small-scale EUV brightenings were proposed as the new members of the nanoflare family, which can effectively contribute to the coronal heating. So inspired by these results, we became more ambitious and tried to search for much more smaller and much more quickly evolving EUV brightenings. And that can be obtained by using much better specially resolved and temporarily resolved observations. And we can achieve either by increasing the resolution of our telescope or going closer to the source. And that's what is special about solar orbiter. The solar orbiter can go as close as to sun of almost 0.29 AU. So we use these very special perihelion observations, closest perihelion observations of HRI UV obtained in 2022 and 2023 as shown here. And as I mentioned already in this set of observations, solar orbiter was almost 0.3 AU away from sun, and this proximity to sun gave the effective pixel resolution of HRI UV observations to be around 100 kilometers. And the cadence of these observations were also better than previously used observation set, and this observation set has a cadence of 3 seconds. So till date, these two set of observations stands the best resolved observations in the EUV passband obtained for quite sun, specifically quite sun ever taken, because for active region we have similar resolution observations from high C. But high C was not targeting as the quite sun type of regions. So by using this special set of observations, we could further detect the smallest and shortest lived brightenings in quite sun. And the number of these events were almost 100,000 in each of these observation sets that we used. And the percentage area coverage over the field of view was almost 0.1% maximum. And this gave us the occurrence rate of these EUV brightenings to be almost 4,000 events happening per second on the surface of the sun. On the full solar globe surface of the sun, if we assume full solar globe to be quite sun. And again, their area and lifetime were limited by the specific set of observations that we used here in this case. So further, when we observe the distribution of these HRI UV brightenings over our field of view of the two specific data sets that we used, as shown here, we find that they are present everywhere over the full field of view, given that they tend to reoccur persistently at specific locations. If you pay attention to these movies, so most of the brightenings are concentrated in regions like this, for example, and also similarly here. So we wanted to further explore the reason for this persistence reoccurrence of HRUV brightenings at specific locations from the magnetic field point of view. And for that purpose, we are using the HRT Phi observation. So HRT is high resolution telescope on onboard Phi, which can give us measurements of magnetic field and Doppler velocities at the photosphere. And for these two, for HRT also, HRT has the same resolution, almost similar resolution as HRI UV, and thus for these two specific set of observations, the pixel resolution of HRI UV as well as HRT is almost 100 kilometers. Now coming to the temporal resolution. For
Nancy,
that,
you have 1 minute.
okay, looks short, but I will try to just finish. So yes, so for data set one, the temporal cadence was 5 minutes, which is not much suitable to study these quickly evolving events. But for data set two, it was 100 seconds, which is not so good as compared to HRI UV. But with HRT Phi observations, this is again one of the best temporal resolution that we can obtain. So I will just skip this slide because this shows how we align HRI UV with HRT Phi. And then I will come directly to one of first point of the result, that to study this reoccurrence, we made these heat maps, which distinctly outlines the regions of reoccurrence. And when we compare this with HRI UV, we see that these small HRI UV images, we see that these small scale brightenings outlines mainly the fine structures within the loops. And thus we concluded that these small scale brightenings are reoccurring within these small scale loop strands, which is when we compare with the simulation previously mentioned simulations, we could find that the simulations also shows the similar scenario where the component reconnection between the bundles of field lines within the small scale loop actually gives this enhanced coronal emission and thus enhanced heating in the EUV channels, which look same as the HRI UV brightenings. Further, on comparison with the line of sight magnetic field maps of these heat maps or the reoccurrence map, which shows the regions of reoccurrence of these HRI UV brightenings, we observe that most of the HRI UV brightenings tend to reoccur at specific network junctions, which are the most predominant regions of interactions of small scale magnetic elements with the major network field. And here I just show one example of such site of reoccurrence where you see the small and the blue contours are the HRI UV brightenings obtained from HRI UV observations. And here are the line of sight magnetogram zoomed in for one of the site of reoccurrence. And these contours are the contours of detected HRI UV brightenings. And here you can see that these small scale minority polarities interacting continuously with the majority network junction patch. And this recursive interaction between the opposite polarities gives the reoccurrence behavior of the EUV brightenings in the lower coronal channels. So with this, I conclude my talk today, that we observed that the EUV, small scale EUV transient brightenings tend to reoccur along the small scale loops. And these sites of reoccurrence are co-spatial with network junctions, magnetic network junctions. And we observed that the small scale flux cancellations in the vicinity of many EUV brightenings. So this small scale flux cancellation at the photosphere is possibly triggering the component reconnection within the small scale loop bundles in the lower corona. And this we can conclude by comparing with the simulation as I highlighted in one of the slides. And so these are the two key takeaways. that the small-scale transient brightenings in lower corona are fine structures within the small-scale loops, and possibly with the previously available comparatively coarser resolution observations before HRI-UV, we couldn't resolve this small-scale fine structure, which are now we are resolving and marking them as HRI-UV brightenings. And these HRI-UV brightenings are possibly triggered by small-scale flux cancellations in the photosphere and at the network internetwork boundaries, which finally triggers the component reconnection in the corona. So with this, I thank you for your attention.
Thank you, Nancy, for insightful presentation. So now we have time for one quick question. There is a question from Arpit Srivastav. Is there any estimation on how much they can contribute to coronal heating compared to other sources such as waves or in general as well?
Yes, so actually there are some studies, and obviously because of limited time, we cannot go through all discussions here in the presentation. So there are some studies which mention that these HRI UV brightenings, not all of them are actually coronal in nature. They can be chromospheric and transition region in nature. So this is a still open question, and some of the PhD students working in our group are looking into this problem, and possibly many other people are also looking into this problem.
Okay, thank you, Nancy. So our next speaker is Munjiba MM, who is a postdoc at the Manipal Center for Natural Sciences. Today they will be speaking about the investigating chromospheric radioactivity losses in non-flaring active region. Munjiba, you have 10 minutes for your presentation, and I will provide you 1 minute warning.
Can you see my slides?
Yes.
Okay.
Yes, we can see it.
Hello all, I'm Munjiba Amam. I'm a PhD student at Manipal Center for Natural Sciences, and I'm working under Dr. Srijit. So we are investigating chromospheric radiative losses. In the study, we are investigating the chromospheric radiative losses in a non-flaring active region. So main motivation came from a study that has been conducted by the Kazachenko and Hudson. They studied sun as a star observation. So the sun as a star has been studied from 1970s, but the contribution of this different magnetic features is not quantified. So different magnetic features are the sources of high UV emission, and biggest such feature is the active region. So the UV emissions during solar flares are well studied comparatively. So the paper by this Kazachenko and Hudson showed that a quiescent active region can also cumulatively radiate significant extreme UVs. So they used sun as a star instrument, but when only one sunspot was there on the disk, so they found that only 1% of the magnetic energy stored in the active region is radiated in EUV from corona. So they did not consider the energy emitted in other wavelength, especially UV from chromosphere. So now, since we have soot data from Aditya L1, which can image the sun, and hence UV radiation emitted by different features can be separately measured, we studied one simple active region which never flared, hence called a non-flaring active region, to estimate how much energy this active region emit in UV during its evolution and decay. So our objective is to investigate how this photospheric magnetic flux and many other magnetic field parameters related to this chromospheric UV emission, and to quantify this chromospheric radiative energy losses as this active region evolves. So the observation was we looked at this non-flaring active region, that is NOAA 14056, for a time period of 8 days from 8th to 16th April 2025. And we used instruments like SOOT, Aditya L1, HMI, AIA, onboard SDO, and IRIS. So we calculated the mean magnetic field, mean unsigned current density, mean photospheric magnetic free energy, etc. from HMI SHARP, and we studied the temporal evolution of UV emission from SOOT, AIA, and IRIS. So earlier we looked at this total emission from this umbral region. As you can see, this umbral region marked in this SOOT MG2K filter. So we found that this total UV emission and this total magnetic field is giving, like, it is decreasing continuously. So this decrease, later we found that this decrease is due to this active region decay. So we came to look at this mean emission and mean magnetic field in this umbral region. So we came across this first plot. As you can see, the left y-axis, you can see the red UV SOOT NB3 mean count, NB3 MG2K counts of umbra, and left right y-axis blue, you can see the mean magnetic field. So initially, the both mean count and mean magnetic field, it decays, and as it evolves, as the UV emission increases, the magnetic field also increases, and later this gives no correlation at all, because as the umbra is decaying. And similarly, in case of mean unsigned current, see there is an initial decrease as the mean count decreases. The mean unsigned current is also decreases, and later it gives no correlation, as it can be due to this active region decay. And in case of mean photospheric magnetic free energy, it as the UV emission increases, like the mean free energy decreases. So this mean free energy, as the UV emission decreases, the mean free energy increases slowly, and as the mean free energy decreases, the UV emission increases. So we have also done the cross calibration of iris, and SOOT can estimate the absolute energy radiated in two spectral band, that is of Mg2H and K lines. So we found the energy radiated in the SOOT patch, and the earlier study that I have mentioned earlier, they have also done this coronal irradiance, that is coming the range of 10 raised to 5 ergs, and you can see this chromospheric emission. We found that it is coming the range of 14.8 ergs per centimeter per second per centimeter square. So in the conclusion part, so we have studied this non-flaring active region for a span of 8 days, and the total magnetic flux, UV emission current, and photospheric magnetic free energy from the umbra decreases systematically as the active region evolves. So with this decrease, we found that is due to this umbral area decrease. So dependence. So we calculated the mean magnetic field parameters, and we found that only this mean photospheric magnetic free energy shows a negative correlation. However, this radiative energy loss in Mg2K and H line is in the range of 13 to 15 ergs per second per centimeter square, which is comparatively lesser than the coronal irradiance that is found, which is found in the range of 10 raised to 6 ergs per second per centimeter square. Thank you.
Thank you, Munjima, for excellent presentation. So now we have time for few questions. Please feel free to raise your hand or post your question in the chat. I don't see any questions in the chat. So I can ask question. So given the combination of SOOT, IRIS and HMI data, what future observations or analysis would help to clarify the connection between this photospheric magnetic evolution?
Sorry, ma'am, can you repeat?
Yes. Yeah. So what future observations or analysis would help to clarify the connection between the photospheric magnetic evolution?
We could get this. You're mentioning the future instruments?
Yes, yes.
Yeah. Actually, if we get a instrument that can derive this magnetic field in the chromosphere, it would be it would be useful to look at the coupling of the photosphere and chromospheric magnetic field, how it is correlated with each other. So it would be nice if we have an instrument to look at this chromospheric magnetic field.
Okay, yes,
Yeah.
thank you very much. Are there any questions for Munjiba? If not, then we can move to the next speaker. Our next speaker is Bablu Mandal, who is a PhD student at ARIS Nainital. Today he will share his insights on spatio-temporal evolution of long-lived supersonic downflows above the sunspots. So Bablu, you have 10 minutes for your presentation, and I will provide you 1 minute warning.
Is my
Yes.
is visible?
Yes.
So hello everyone. So this is Bablu Mandal from ARIS Nainital. I am a PhD scholar here, working under the supervision of Dr. Krishna Prasad. So today I'll be talking about sunspot-specific flows in the solar atmosphere. So this is the overview of my talk. I will initially introduce you to the topic supersonic downflows, followed by data we have used for this study, methodology we employed for this study, and the results and a concise summary. So as promised, let's start with the introduction. So if you look at the spectra, then downflows are observed as redshifted component in the spectral line. So here is a typical spectra focusing on active region 11836. So it is here. You can see the spectral image where x-axis is denoting the wavelength, y-axis is denoting the solar position along the slit. So here you can see there is like bulge-like structure on the longer wavelength. So these are the typical signature of these downflows. So if you compare the average spectra from quiet sun as well as like umbra region, then you can find like in quiet sun as well as umbra region, there is one component present in both regions. So that is called main component, but one specific component is only to the sunspot that we are called like secondary component. And usually the speed of this secondary component is the higher than the local sound speed. So they are called like supersonic downflows. So they found like 80% of the sunspot, including umbra, penumbra and both regions. Sometimes their signature can also be found in the chromospheric line, like magnesium K and H line. Here you can see the signature, typical signature. And they are very intermittent and often recur at the same location. So their spatial scale is like few arc second and repetition time scale like a few minutes to few hours. And based on their lifetime, they are like two types, short-lived types. So they are very intermittent type. The lifetime is like few minutes. And another one is the long-lived type. Their lifetime is like order of several hours. So from now, I will be only talking about this long-lived type downflows. So for this study, we use IRIS repeated raster mode dataset. So the aim of this study is to better understand their spatiotemporal evolution in the solar atmosphere. So this navy box is showing the IRIS SGI imaging data field of view, and green rectangular box is showing the where we have like iris spectral data. The cyan color box here is showing the where we found the signature of downflow. And typical signature of downflow is shown for one raster is shown in here. So coming to the methodology part, so initially we bin the data, we bin the data twice in the y direction. So here after binning at this location, typical spectra is shown here. Then what we do, we do like triple Gaussian fitting. So here is the combined spectral fitting. So we constrain our 3 Gaussian to this these constant parameters are there. So here 3 components are shown here. So from now we will be only focusing on this secondary component. So after spectral fitting, we do it like we created the intensity map, and within that cyan box I previously mentioned, we studied the further evolution of these downflows. Similar spectral fitting for oxygen lines 1399 and 1401 is for one typical spectra for 1401 is shown here. So here the spatiotemporal evolution of this downflow is shown here. First 3 panel is denoting the intensity map from spectral fitting. Third one is from the imaging data of SGI 1400. So here this contour is showing the umbra penumbra boundary. So initially the downflow signature can seen in penumbra region as well as umbra region. With advancement of time, the in penumbra region the signature fades away, and in umbra region the downflow signature getting stronger, and eventually this appeared to be a single structure split into 2 parts, and at the end of the observation only 1 part remain. Here is the movie of the evolution. So you can see like the initially there is like in penumbra the downflow is there, then it moved to the umbra region, the downflow getting stronger. Eventually this downflow is split into 2 parts, and at the end of the event only 1 part remains. So we try to figure out what is the cause of this splitting. So we compare with AI images. So here we can see like this is the umbra penumbra boundary. So near to this region, there is sudden brightening seen in AI channels, and you can see like there is this around timestamp 1955. There is a brightening. So this brightening is shown in all other channels, indicating there is a multi-thermal plasma present in that location. So we also do the magnetic field extrapolation to find further information regarding this. So here results from non-force free field extrapolation is shown here. So in non-force free extrapolation in photosphere, we consider there is a non-zero Lorentz force is there. So here we consider like two magnetogram before the splitting event around 1936 UT, and one is after the splitting event around 2012 UT. So magnetic field extrapolation revealed that there is a fan spine topology structure near to the sunspot. So in first panel there is like HMI continuum image is showing here. Here is the umbra penumbra, and near to the sunspot there is this magnetic fan spine topology is there. So there are 2 magnetic topologies. One is like open field lines that are shown in blue color, and there is like fan spine topology, and you can see like the magnetic polarity values here. So and also like in previous image we saw like there is brightening in AI images. So that 1955 brightening images are overplot in here. So you can see like it is near to the base of this fan spine topology. And if you compare like after before the splitting and after the splitting, so there is like magnetic field topology change in this fan spine topology. As a result of this magnetic field topology change, as well as the multi-thermal plasma, we can say that there is like some reconnection is going on. As a result, we see the splitting of the downflow. Before this splitting, we also observed an anomalous motion of the loop foot point. So here, 4 panels showing like first panel is showing the high-speed downflow component. Second panel is showing the low-speed downflow component, and the other two component is this SJ 1400 is looking at the transition region, and SJ 2796 is looking at chromosphere. So I would like your attention to this panel C. So here in first like timestamp 1933, so you can see like the two contours are plotted. So one is like corresponding to like 10 dn values, and other is like higher dn value like 65 dn. So this contour were plotted in following timestamp. So, and this higher value is higher dn value contour also plotted in other panels. So here you can see like at starting the structure is here, and with advancement of time there is a north motion, solar northward motion, then it moves toward the eastward, and this can like continue around like this time. Then
you
hello.
have 1 minute.
Oh, okay. Thank you. So like here we can observe the motion towards the solar north. Then it after some time it is coming back. So from the movie it is more visible. So so initially the structure is here, and you can see the structure move towards solar north, then it moving towards the eastward direction. This similar pattern can be shown in like these spectroscopic channels, as well as like lower atmospheric channel like 2796. We compare like this iris spectroscopic observation with AI observation, and we found that the downflow morphology is linked to the change in the coronal loop morphology. So when there is penumbral downflow present, we saw this structure, but when penumbral downflow fades away, the structure also vanishes from the site, and also we can see the evolution in the AI 170 channel, the loop evolution. For timing, I am skipping this video. So we also, find the average properties of these downflows. Like we found like speed is, there is slight increase in the speed, and density is almost remain same for the whole duration, and mass flux is also like remaining same. We compare this study with previous study, and the average properties are like aligned with the previous studies. So this is the summary of the talk. So like we use repeated raster mode iris observation to study this spatiotemporal evolution of this downflow, focusing on active region 1, 2, 1, 3, 5. So we see that downflow are initially in the umbral and penumbral both region, but over time penumbral downflows are getting weaker, and in the umbral region it is getting stronger, and eventually that appear to be single structure split into the two segments. And from the extrapolation as well as the AI images, we found that the magnetic reconnection near this site is the most probable cause of this splitting. And the downflow morphology is linked to the change in the coronal loop structure. And also we observed area motion of this foot point of within the sunspot, and the average properties we derived for this event are consistent with the existing study. So thank you.
Thank you, Bablu, for an insightful presentation. So we now have time for a few questions. There is a question from Isha Sharma. Is that brightening an ejected plasma blob in the AI image you showed in slide 11? Or is that magnetic reconnection point at that height?
So like there we see like brightening in the AI images. So like we see in if you look at like sorry. So in AI images, like in 171, you see the brightening, as well as like in other hotter AI channel, you see there is also brightening at that moment. So it's most probably uh, there is like multi-thermal plasma is there. Most probably there is some reconnection going on at that site.
Are there any questions for Bablu? I have a question.
Yes.
So is there any way that we can find out these downflows in any other chromospheric lines, such as carbon 1 or oxygen 1?
In magnesium line, there is sometimes there is signature. So like if I move to this, like in magnesium, like K and H, like there is like signature for people found in signature there. Sometimes there may have signature in the chromospheric line, but sometimes they don't have like signature. So they usually their signature can be found in transition region line, like silicon 4 and oxygen lines.
Okay,
In lower line, sorry,
not in carbon 1 or oxygen 1.
no.
Okay. Sorry, you were saying something. I just stopped in.
I mean, in magnesium line, you can see sometimes signature there.
Okay.
For this case, we see like intermediate signature of in magnesium K and H line.
Okay.
But
Thank you very
no
much.
signature in carbon 2. Yeah. Thank you.
Okay. Thank you very much, Bablu.
Yeah.
Any other question for Bablu? If not, then we can move to the next speaker. Our next speaker is Rohan Bose, who is a PhD student at Aries, Nainital. His talk today will focus on microwave polar brightening and its connection to polar coronal holes. So Rohan, you will have 10 minutes for your presentation, and I will provide you 1 minute warning.
Okay. Am I audible?
Yes.
Can you see my screen?
Yes.
Hi everyone. I am Rohan Bose, a PhD student at ADIS, working under Vaibhav Pant from IIT Delhi. In this particular talk, I will be talking about the microwave polar brightenings and its connection to the polar coronal holes. These are the collaborators for this particular work. So without further delay, I can proceed. What are these what are these microwave polar brightenings? So this is a Nobiama radioheliograph image taken at a 17 gigahertz band, the image of the sun from 1st January 2017. So here at the south pole of the sun, you can see there are patchy brightnesses. So these brightness are known as microwave polar brightenings, and they are persistent brightenings. So like if you see in multiple days, you can see this the existence of these patchy brightnesses in every image. So in the North Pole also they are there, but due to the tilt angle of the sun towards this Earth, this cannot be seen in the North Pole. So the study of these micropolar brightenings are still in progress for greater than 40 years, but still their origin is not fully known. So what we know up to now is that there are bright features intrinsic to the poles, and they are associated sometimes associated with this white light faculae, and some authors suggest that they are associated with the strong unipolar magnetic field lines in the coronal holes. Recently in 2017, Sailhost et al. Gave a model where they tried to explain these microwave polar brightenings as small magnetic loops. So in this particular study, we will also look into that aspect. So this is the data we have used for this study. So in background, you can see the microwave image and the UV image of the sun, and you can see that at where the polar brightening was there was some coronal holes, polar coronal holes were there. So the November radiolograph data is available from 1992 onwards and up to 2020. And so we have only used the 17 gigahertz, but it has also 34 gigahertz channel. And then for magnetic field data, we have used Wilcox Observatory magnetograms from the for the same period, and this AIA we have used from 2010. And we have used only the 193 angstrom channel because in this particular channel, this coronal holes look in more contrast. So, to probe the these brightenings, we first tried to extract the brightness profile of the these polar brightening structures. So for that, we plotted the brightness profile from center to the limb of this, and we started from the west limb, and we went towards anti-clockwise, and then 1 degree apart we created these lines. For each line we have a this brightness profile similar to this, where this is the out of the limb. As you can see, this is minus 950 oxygen, and this is closer to the limb, but this profile only shows up to this red dash region. So, like for probing only the polar region, for each polar region, we have taken plus minus 30 degree left and right, and for all the 60 profile, we created a average profile that is also similar to this, and then we fitted this average profile with this empirical relation. So after fitting, the peak of this fitted line is what we term as the intensity of this polar brightness. So this red and blue line shows the this radio and this photospheric limbs. So, and now when we do the same example for this long-term data, we get a value for this polar brightness for each poles for each day, and from that we get this plot. So here the values are this polar brightness intensities and normalized intensities relative to the quiet sun, where quiet sun is taken as 10,000 Kelvin, because in the radio images they are normalized like that. So, but you can see some asymmetry between this north and south pole regions. So here you can see that the period are a bit different, and also you can see in the north pole from 2013 to 16 there was a plateau at the minimum, but in case of south pole there was no plateau. And also that is similar in case of 2001 to 3 period, there was a plateau here but not here. So it shows that there is some hemispheric asymmetry between these two the north and south hemisphere of the sun. And also like this particular feature, as you can see that it has a 11-year cycle, but it is anti correlated with this sunspot cycle. So here you can see the position angle versus time plot, where this 0 degree is the west limb, and this this 90 degree is north pole, and then 270 degree is the south pole. And you can see at the 90 degree and 270 degrees, you can see the brightnesses, and these are the polar brightness patches we are talking about. And you can see some dark regions which are the minimum positions, and also in the equatorial region you can see these butterfly diagrams due to the sunspots. So, as our title suggests, that we tried to probe the connection between this polar brightness and this coronal holes. So we tried to detect the polar coronal holes. For that, we use the SPOCA catalog to get the boundary of the coronal holes. So this is a map of using SPOCA catalog. We plotted the coronal hole map, and we only considered the 90 degree to 60 degree region to extract the polar corner hole counterpart, the area. For the area we counted the pixels which are in 1, because the other regions are 0. So and we did the same exercise for like 10 years data from 2010 and 2022 20, and then also for that up to 2025 to for the visualization to increase. And then you can see that here also you can see this periodic nature for the this corner hole area variation. And here also you can see that there are some differences in the periodicities, and also the plateau I showed you for the polar brightness curve long-term variation from 2013 to 15 16. So it is also present here, and in case of South Pole it is not there. So then we plotted both of them in a same plot, and along with the polar magnetic field, which we calculated from the Wilcox magnetogram data. So so then we calculated the cross correlation factor, which came around 0.67 between the polar brightness and the corner holes for North Pole, and for South Pole it was 0.63, which is sufficiently strong to consider it that they are correlated. And for the this magnetic fields with the polar brightness, the cross correlation was very strong, 0.91 for North Pole and 0.88 for the South Pole. So
Rohan,
yeah,
you have 1 minute.
okay, yeah. So this tells that this polar brightness has a magnetic in nature, and there is some connection between with the corner holes. So this is the this butterfly diagram where this sky blue region, so the magnetic field, polar magnetic field regions of 0.5 and 1 Gauss, and you can see that they enclose the bright polar bright regions. So here you can see, so for a particular date, we plotted the polar coronal region and overplotted them with the radio contour. So this red, blue, and yellow are different temperature contours, and you can see this at the green points they overlap on this UV counterparts. But in case of white regions, they don't overlap on any UV counterparts. So then when we and for 1 year data, you can see this movie. So there are some days where the correlation is more, and for some days there that is not that much. So now we got two kind of association. So here you can see some loop like structures underneath this contours of radio here. And also there are some regions where we see coronal jets at the regions of this brightness. So we found these two, these small scale loops are in literature they are termed as coronal bright points. So we searched for 1 month data, and within that in 60 to 70 data we found this correlation. Majority of them were CVPs and some of them were coronal jets. So then we tried to explain them the radio polar radio brightenings as counterparts of the CVPs, but the jets can occur when the kilogauss open patches in the polar regions reconnect with the CVPs and give rise to the coronal jets. So these are the key takeaways. We got 15 plus minus 4% of the excess temperature for both the poles, and then we saw a hemispheric asymmetry, and then we saw the strong correlation between the corner holes and MPBs. And then the two cases we found, one is this CVPs and then cornel jets. And for coronal jets, basically in case of CVPs, we think that that is due to the free emission, but for coronal jets, there can be a guided synchrotron emission too, which is playing role. So that's it. Thank you. If any question, you can feel free to ask.
Thank you, Rohan, for excellent presentation. We now time for questions. Any questions for Rohan? I don't see any questions in the chat. I would like to ask a question. So,
Okay.
given the association of polar brightening with small-scale jet activity.
Yeah.
What further observations or simulation would you recommend to study the underlying magnetic dynamics?
So first of all, we should have this temporal analysis, because for this case only we have studied a particular timestamp. But then if we see for particular jets, the temporal variation and the corresponding radio variation, we can be surely confident that these jets are giving rise to these radio emissions. So that is the first case. And then like if there is some like in the polar region, if there in some cases there are some magnetic field data, we can try to probe those also from HMI.
So, can we say that the polar brightening could be served as a proxy for changes in the polar magnetic field?
Excuse me, can you
Um,
repeat?
do you suggest that the polar brightenings could be served as proxy for changes in the polar magnetic field or kernel hole evolution?
Not directly that, like they can be one of the contributors, but the like that is a different question if that are the main contributors or not. Because in our case, what we try to probe is that the polar brightenings also show 11-year cycle, so they are a part of those systems. So we don't exactly know they are the main contributor to the variation or not.
Okay, thank you very much, Rohan.
Thank you.
So our next speaker is ISHA Sharma, who is a PhD student at Banaras Hindu University, Varanasi. Her talk is focused on formation mechanism and dynamics of spicules and jets in the solar chromosphere. So Isha, you will have 10 minutes for your presentation, and I will provide you 1 minute warning.
Thank you. Good afternoon to all. Is my presentation visible?
Yes.
Okay, so today I'll be talking on the most prominent features that we see in chromosphere, which are called spicules and jets, and how are they formed in the solar chromosphere. Basically, this will be the outline of my talk, where I will first show the observations of spicules and jets, then address some primary questions, then talk about how the spicules are formed and jets are formed. So this is the observation taken by Hinode SOT, Solar Optical Telescope, which is a Japanese mission. And you can see some very ubiquitous features on the solar limb. Then another this observation shows again the solar limb, but is my cursor visible? Okay. So these structures, these brightenings, transient brightenings, and the plasma ejections that you see is the another observations from the same solar optical telescope on board Hinode. Now, what is the difference between these two kinds of observations is that these features that you see at the limb, these very fine grass-like features, they are called as spicules, whereas these structures at the limb, which have these bright footpoints and collimated ejection of plasma from them, these are called as jets, and both of them we want to see what are the formation mechanism of spicules and the jets. Now the primary question that we will address apart from the formation mechanism is how these spicules and jets they evolve over time, and what are the typical velocities and energy deposited by them in the atmosphere. So previous talks have talked about how there are magnetic fields and they are responsible for different kind of activities, and what could be the reason for the heating of the chromosphere. So basically, when we study the spicules and jets, they kind of lead us to these solving these kind of problems of chromospheric and coronal heating. I'll move to the formation mechanism. So, the motivation behind these studies is there are statistical studies done previously. This study by Zhang et al. It shows that the mean height of spicules, which are around 5 megameters to 9 megameters, and lifetime of around 2.5 to 1.8 minutes. We want to understand that kind of physical mechanism are occurring on the level of photosphere, chromosphere, which are giving rise to these kind of heights and lifetime and the velocity of species observed. So there are studies which suggest that there are high frequency waves trapped in the photosphere, which could carry enough power when they propagate upwards, which could give rise to these kind of specules. So we want to investigate what exactly is the mechanism of the propagation of these waves and formation of specules. So we try to utilize the magnetohydrodynamic simulations for this study. In our simulation, we have considered this model of expanding magnetic flux tube, where we have given the torsional and longitudinal velocity perturbations to this flux tube, and we have studied it for 14 hours of MHD simulation and see how the specules evolve over time. Now, these open expanding magnetic flux tube allow uh, the P mode linkage by which these waves travel up in the upper atmosphere from photosphere to the upper solar atmosphere. And we have taken into account the gravitational stratification and radiation loss as well in this study. And this structure here in the right side, you see the evolution of these specules when the waves travel through these inside this flux tube and towards the upper solar atmosphere. Now, these are the results that we obtain. This is the density plot variation of how height of the specules vary with time, and we see that in this with the perturbation wave period of 600 seconds, we have in the simulation achieved the significant height of more than 10 megameters. And these are the other along with that 600 seconds, we have taken the perturbation wave of 10, 25, 50, 75, 100, and 150 seconds. And for all these perturbation wave periods, we have calculated what are the heights that are achieved by the specules. And we see that a significant amount of height which are in accordance with the observations are being achieved here. And even more than that, like in for 150-second here, the heights achieved are 20 megameters, and mm, and the heights are not just for very small amount of time, which is 80 minutes. It is much more than that, which is for all over the simulation time of 14 hours, which clearly suggests the uh, uh, presence of specules in the solar disk for in the solar limb for such longer amount of time. This is a comparative plot that we have taken for different wave periods, and it suggests that the peak heights that are achieved for a particular wave period and uh, what are the heights that are achieved at the 14th or the end of the simulation 1800 minute, and we have seen the difference, that how much is the peak height and the difference between the peak height and the height of speakers attained at 800 minute, where we can uh, try to optimize what are the wave period that could give us the optimum height at that uh, wave period basically. Now, these are the energy flux deposition that we have achieved from our simulation. So in the literature, we have found that 10 to the power 7 of a centimeter square second is the energy budget required for chromospheric heating. Through our simulation, what we have achieved is around 10 to the power 9, 10 to the power 10, and 8, which suggests that significant amount of energy is being deposited by specules, which could be responsible for chromospheric heating. Now I will move further with the formation of jets in the solar chromosphere. And here is the, I don't know, okay, so yeah, this is the movie that you can see. Uh, these are the jets observed in calcium 2H filter solar optical telescope. This is the filtergram image. This is an edge enhanced image where we can see multiple small scale jets evolving from the bright foot point, and this is the running difference image of the jets, which suggests there is very fast motion of multiple jets which are evolving over time. So we want to understand that what are the physical mechanisms giving rise to such fast motion jets from the same bright spot point, and uh, we understand that the collimated ejection of these plasmas from identified foot points, we call them as chromospheric jets. The mechanism responsible for the formation of jets is understood as magnetic reconnection, and they are significant contributors for chromospheric heating, and they could be understood as the prominent features that could help us understand the coupling of the atmospheric layers. A recent study by Singh et al. In have proposed a three-dimensional magnetohydrodynamic model for the formation of these jets, which have so previously there were two-dimensional models, but
Isha,
3D model have not been studied previously. So this time they suggest that there are
Isha,
these twisted.
you have 1 minute.
Okay, thank you. So there are at the level of photosphere, there are twisted magnetic flux tubes, which when evolve in the upper solar atmosphere, they reconnect with the ambient vertical magnetic field and give rise to magnetic reconnection. But we know that magnetic reconnection happened between the emerging magnetic flux tube and the vertical fields. That's what is the difference between that 2D reconnection model and this 3D model is that we this magnetic flux tube, twisted magnetic flux tube, can have various different orientation, which can also account for different kind of morphologies that the jets can achieve. Now, these are the simulation results that we obtained from this model, and this is the jet morphology from the y direction. This when the magnetic field reconnection takes place along this flux tube, and then this is the morphology that we take when it is along this axis. So one morphology of jet will be seen when reconnection takes place along the flux tube, and another is the perpendicular to the flux tube. So these kind of jets are obtained. This is the observation of the velocity of jets that can be achieved, which is around 40 kilometers, 2 kilometers, 6 kilometers. And these are the velocities which are obtained from the simulation, which is very well in accordance with the velocities obtained from the observations. So this is basically the physical process that is taking place between the twisted magnetic flux tube and the ambient magnetic field. So to summarize the whole talk, I would say that what we wanted to understand is what are the different, whether the specules and jets have different physical mechanism or same. So what we have found out from our simulation study and the observation that specules are basically formed by the propagation of MHD waves through the perturbations present at the level of photosphere, whereas jets are getting formed by the successive magnetic reconnection between constantly evolving the twisted magnetic flux tube and the ambient magnetic field present in the solar atmosphere. Both of these processes are unifiedly important because they are significant contributors in solar atmospheric heating and in the understanding of acceleration of solar wind. And what we also find out that the high frequency perturbation present at the level of photosphere can significantly give rise to taller specules, which could be more than 6 megameters. These are the key references, and that's all.
Thanks, Isha, for excellent presentation. So we now have time for a few questions. So there is a question from Rohan Bus. Can you comment
Yes.
on physical counterparts of the perturbation of different periods you used in the simulation?
Okay, physical counterparts. So basically, there are granular motion which give rise to these kind of waves. So, like, what is, I don't understand that what is the physical counterpart of waves means. I don't understand. Like, what physical mechanism is giving rise to these perturbation waves? That's what you're asking.
Rohan, could you please clarify your question? You can unmute
Yes,
yourself.
yes,
Yeah.
yes.
Okay, so these granular motions in the photosphere. So the first talk, when in the session one, the first talk they have presented that how there are motions in the photosphere. They also have talked about. So there are granular motions in the photosphere which give rise to these kind of perturbations are already present in the photosphere. So some can escape, some don't escape, and there needs to be this configuration of flux tube by which these waves escape.
There is another question from Arpit. Your simulation results show the energy flux of specules 2 or 3
Yes,
orders of magnitude greater than
yes,
required for
yes,
chromospheric heating. Does that
yes.
mean the specule alone can heat chromosphere seen in the
No,
observation?
mm, not necessarily, because these are very localized. Specules are local. They can be in large numbers, but during in that transient minutes of time, they are depositing those energies. But given the scale of whole solar atmosphere, there needs to be much more activities and features that um, and many more mechanisms required for the overall sustained heating. So chromosphere could not sustain heated all the time.
Okay, thank you very much, Isha. Uh, our next speaker is Sandeep Dubey, who is a PhD student at Udaipur Solar Observatory, PRL. His talk today will focus on chromospheric flashes in a solar pore, insights from multi-line spectropolarimetric diagnostics.
Can you see my screen?
Yes.
And you can also hear me, right?
Yes.
Okay, so thank you, everyone. I'm Sandeep. I'm a PhD student here, and I'm going to talk about pores and flashes, so which is a rather unusual combination, I'd say. And the background image you are seeing is from the SST, which is the 1 meter solar telescope, and this is the typical photosphere that you see. So you have these big sunspots that are basically two part. You have the dark umbral core, and then you have this filamentary penumbra, and then you have the small scale granules, and you also have the pores. If you could follow my cursor, these small scale structures that lack the photospheric penumbra are the solar pores. So these are also strongly magnetized regions, relatively cooler than the quiescent photosphere, which is the granular background. We are going to talk about flash activity, which is happening in solar pore, which was not possible to do, I think, maybe 10 years ago, because these structures are already small. And if you are going to study the substructure within these structures, you need high resolution telescopes. So, which is now possible with the advent of big solar telescopes. So, just to introduce the problem itself, solar pores are small scale magnetic structures. Their initial stage of the sunspot, so the later on penumbra forms in and around the sunspot and in and around the pore, and then it forms, it kind of translates to a mature sunspot. And magnetically, they are basically flux bundles with predominantly vertical magnetic field. Size-wise, they are roughly 1 to 6 megameters, and they can persist from few hours to more than a day. And if you go to the substructures, they are pretty much similar to the umbral core of a sunspot, which is you would see umbral dots, which are small scale convections in between the magnetic gaps, I should say. And then you have light breezes that basically separate the pore or is responsible for the splitting of the sunspots in later stages. And velocity-wise, you see strong downflows around the pore boundary. And flashes are rather well-known entities. So when you go to the chromosphere and see the intensity images, especially in the calcium 2 line, there are small scale intensity enhancement that keep on appearing inside the umbra. And if you could follow the cursor, the small dots that you see inside this umbra are the flashes. They keep on happening inside, pretty much inside every sunspot, and they have both plane of sky and line of sight velocities that are of the order of 10 kilometers per second. And these flashes are periodic, roughly with 3 minute period. Why they happen is because you have photospheric oscillations that channel to the upper layers, and because of the density decrease and a number of factors, you have shocks that develop, and these flashes are heating associated with the shock fronts. So this is like an overview of uh, these two things that we are going to talk about. And this work is basically, I wanted to see how these flashes appear when you start going to smaller magnetic structures. So sunspots are well studied. They're big structures. You know how wave phenomena are taking place, what kind of physical attributes are associated inside the sunspot. But how does it look like? Or does it even look like when you go to smaller structures, such as a pore or maybe isolated magnetic elements? So this study was motivated by this simple outline itself. So the observation that we used for it is multi-line. So we used multiple spectral lines from SST, all the way from photosphere, which is 6302. It's a famous Inode line. It's magnetically sensitive, strong line. And then you have calcium 2, which is the chromospheric line. So all the way from photosphere to solar corona, which is basically sampled by the AIA UV channels, we took pretty much everything that is available. The idea is to see or kind of understand the flashes, the associated events, or associated stratifications across these different layers. How does it show? And the observations were polarimetric, which means in iron 1 and calcium 28542, IQUV were there. So we have intensity observations. On top of that, we also have polarimetric observation. The advantage would be to you can also estimate the magnetic properties other than velocity and temperature, and you can kind of make a holistic picture of what is actually happening there when a flash happens. So just to give you an overview of how it looked like, the left image is basically the HMI full disk intensity image showing the NOAA 12858 in which the flash happened, or basically the pore appeared on 2021, August 19. And the right panels are a snapshot of the small FOV all the way from photosphere to transition region, which is IRIS 1400. We studied focused inside this. And if you see the, 10 by 10 arcsecond, and if you see the intensity image time series, you would see multiple flashes happening inside the pore. And this keeps on happening. So this is happening at the calcium 8542 line core level. And if you take a snapshot of it, you would see multiple flashes that are appearing predominantly in the left side of the pore. Some of them are also on the right side, but majority of the flashes are on the left side. So we wanted to understand what is the physical condition that is forcing the flashes to appear mostly in the left side. And to do that, we took the iron 1 line, which is the photospheric line, inverted it all IQUV, and got the temperature, velocity, and magnetic structuring of the photosphere. So if you see the global picture, not much is changing. The pore is pretty much similar over the course of more than 1 hour. And velocity wise, you have strong downflows in the near neighborhood of outside the pore. Magnetically also does not change much. So we took two different regions. One where the flashes are appearing predominantly, which is outlined by the box in white, and one that is predominantly, that has photospheric structures, and you do not see flashes that often in that portion of the pore, which is the sandbox. And if you compare the magnetic and velocity properties there, this region, the region where flashes are appearing was cooler, roughly 400 Kelvin cooler than this quiescent portion of the pore, had a stronger magnetic field, roughly 250 Gauss stronger, and the field line was more inclined, which is favorable condition for channelization of the perturbations in the photosphere. And offlow is there. So this offlow is basically taking plasma to the chromosphere and above. So this is the photospheric layer, or a comparison of how photosphere behaves at a location where flashes are frequently occurring and at a location where it is not. And then if you see the power distribution map, because flashes are periodic events, so they have to be associated with wave motions. So if you see the power distribution in 3 and 5 minute bands, which is 3 minute why, because it's predominantly chromospheric power, and 5 minute because it's predominantly present in the photosphere. So if you see the spatial distribution of power in 3 and 5 minute bands across different layers of the atmosphere, all the way from upper photosphere to the maximum height of the calcium 2, which is 1300 kilometers roughly. Photosphere, both 3 and 5 minute powers are co-spatial with the flash location. But if you go to the chromosphere, 5 minute power channels out of the pore, and 3 minute power is more or less co-spatial with the location of the flash, which is the period of that. So this is the power structuring of different layers, and its co-spatiality with the flash location. And if you go to the chromosphere and try to get our different attributes, which is the temperature, LS velocity, and BZ, to do that, what we did is we simply inverted this line, using Nicole, which is a non-LT inversion code. The stocks I and V, because Q and U are a bit noisy for this observation. So we got line of sight magnetic field in the chromosphere. Sorry. And then we had temperature and velocity. And if you see the time series of it, which is shown in the right panel, you'd see that whenever a flash is occurring, which is highlighted with the cyan box, you have consecutive intensity enhancements that you can track across different layers of the atmosphere. You also have temperature enhancements that you can track. And we could track the flash associated heating up to 50% line depth of the calcium 2, which is roughly 400, 500 kilometers on the photosphere. So these flashes start to show up above T minima, and then you can see them distinctly in the chromosphere, but not very clearly in the photospheric layer. And the important thing that happened here is, if you see the velocity structure, these downflowing flanks are something that are very unique. So this is, so you have the central upflow, which is taking the photospheric and the chromospheric plasma to the upper layer when a flash happens. But then there is a return flow, which is simultaneously present at the same location. Sorry, at the same time. So in order to check that whether this kind of velocity structuring is unique for a given flash or is it universal, we selected 12 different flashes, and this velocity structuring is more or less similar in the chromosphere, which is kind of interesting. And the associated temperature enhancement in the chromosphere was of the order of 2000 Kelvin at log 2 minus 5, which is roughly 1000 kilometers. So chromospheric temperatures are much more enhanced, I mean, with increasing height. And another thing that happened is, if you see the time series movie, you would see that whenever a flash happened, there are multiple intensity disturbances that propagate out of the pore, and these are running waves. So historically also they are called running penumbral waves, because they are associated with penumbra of, they are observed over penumbra of a sunspot. But when you have a pore, you don't have a penumbra. So we had a dilemma what to call them. So we simply call them running waves because we don't have a penumbra. But morphologically, structure-wise, and velocity strength-wise, they're pretty much similar to what is happening inside a sunspot or observations inside a sunspot. So what we did is we simply took, once again, multi-height analysis of how the velocity structuring of these waves are changing.
Sandeep,
Yes.
you have 1 minute.
Sure, thank you. So we carried out multi-layer analysis of these running penumbral waves, and in the chromosphere, the velocities are of the order of 10 kilometers per second, and they kind of get damped when they travel. So you see stiffening with increasing radial distance, and after a few arc seconds, you don't see it, simply because these waves are traveling along inclined field line, and they kind of leave the formation height range of the calcium 2 at atomic species. So then the next thing was, like, we also had transition region and AIE filters. So we tried to see how these flashes show up in transition region. And so for that, what we did is we simply look into the time series of the intensity images. And you do see that flashes are prominently appearing in calcium 2 filters, which is Z542 and calcium K, and not so prominently in S beta, especially in the intensity image, neither in the iris 1400, which is the transition region filter, not even in the chromosphere, not even in the photosphere. But if you see the spectral response, which is the time evolution of the spectra, you would see that whenever a flash happens, you can see its signature explicitly in the line profile, especially in the blue wing or close to the line center. And Stokes V, which is the proxy of line of sight component of the magnetic field, shows apparent polarity reversal simply because the line core goes into emission. Calcium 2K is already enhanced because the line core of that particular line is already enhanced because we are in a magnetically strong region. And whenever a flash happens, you have additional heating. So core shows additional heating, which is pretty much, consistent with the observational understanding of how it should behave. H beta is something tricky. So H beta line has a formation height of a very broad range. So even if you have a localized heating due to a shock front in a particular slab of the chromosphere, the response is not localized in the spectra. So the entire spectra shift because of this broad formation height of this line. So wherever, basically this is the spectral response in multiple lines associated with the flash in the chromosphere. And to summarize everything in one line, we have carried out the flash study over multiple spectral lines that basically sample all the layers from photosphere to chromosphere, with a prominent understanding that the flashes in the pore are confined to the lower and mid chromosphere without a significant signature in photosphere and transition region, which should be the case because it's magnetically not that strong compared to a sunspot. So this paper is published. You can have a look at it. And thank you very much.
Thank you, Sandeep, for an insightful presentation. We now have time for a few questions. Any questions for Sandeep? I have a question. So,
Yes.
did you notice any correlation between the Stokes V reversal and the velocity or temperature patterns of the flashes, and
Yes.
that might indicate about the magnetic configuration?
Yes. So if you see the magnetic configuration that I can maybe show you where it should be here. Yes. So if you see the magnetic BG stratification, so this panel shows the BG stratification across different optical depth height, all the way from -3 in the optical scale to -6.5, which is, I should say, in terms of geometrical height, if you ask me, it's from 400, 500 kilometers all the way up to 1200 kilometers. The BG does not change much, so that's a problem. Even when a flash happens, your background magnetic field is not changing much, especially at least. But if you see the line plots in this panel E, whenever a flash happens, we do see that magnetic field goes down, and the velocity structuring is a bit complicated. So magnetic field is altered by the flash. This is kind of well established in sunspots. This is the first time we are showing it in a pore. But the velocity signal is a bit complicated because if you see these images, especially from J to K, you have a central upflow and then you have a downflowing flank, which is co-temporal. And we also had a time series of this in the paper that shows the cadence of this particular observation, which was 37 seconds, is not sufficient enough to capture the evolution of the flash. So you have a flash at t0. If you move one frame, which is 37 seconds, and move one frame ahead, you don't capture the evolution. So I should say, in order to capture this entire dynamics of how magnetic field and velocity structuring is changing when a flash is happening, and how does it show up in Stokes field spectra, we need a much faster cadence than the cadence for this particular observation.
Okay, thank you very much, Sandeep.
Sure, thank you.
So, thank you all for attending this session and for excellent presentation by our speakers today. We have explored a range of topics from supersonic downflows above sunspots, chromospheric jets, spicules, EUV brightenings, and microwave polar brightening in active regions. So we now move into the session summary and discussion segment. This is an opportunity to ask additional questions to our speaker, also to reflect on broader challenges, implications, and future directions in solar physics. I encourage all speakers and participants to actively share their thoughts as we discuss these exciting topics. We will begin this session by going through unanswered questions from the chat before moving on to the additional discussion. So I hope you can see my screen.
Yes, we can.
Yes, thank you very much. So there are questions for Nancy, and they were all, most of them were answered. So I was wondering whether Nancy would like to say a couple of words about these, or do you have any more information to add to?
Yes, sure. I can just quickly summarize the questions and then people can ask in between any related questions. So Aditya asked about the chromospheric counterparts because that was the last question, the question asked by Arpit, and I answered that for coronal heating, we first, some papers mention that these, some parts of these EUV brightenings can be chromospheric, and definitely then they cannot contribute to coronal heating. So in that respect, Aditya asked that if there are already studies where we see the chromospheric counterparts and study them in a better way. So definitely there are already few studies with iris lines, and recently from EUI team, myself as sub coordinator, also conducted some joint observations of solar orbiter with ground-based observatories and also with IRIS to address these questions as Aditya is asking, and maybe on similar lines, Siranjana asked that if there are any prospects of using DKIST. So yes, sure, definitely, it's very nice inputs. And again, the same, we are continuing to take a lot of observations, as many as possible, of solar orbiter with ground-based, with IRIS and with SST DKIST. So there are a lot of observations which definitely should be explored in this context. And then maybe Arpit asked the continuation of his previous question, that to address the problem of this coronal heating, he suggested that we should definitely have a simultaneous high resolution cooler pass bands and also hotter pass bands, so that we can map the full atmosphere at high resolution as much as possible. And definitely that's the ideal way we should go. But the advantage or the highlight of HRI UV that it is the best resolution possible in EUV channels as we have, and we do not have the similar resolution in any other EUV passband. For example, AIA is coarser resolution and also SPICE is slightly coarser resolution. Definitely from chromosphere, we can match the resolution from IRIS and ground-based observatories, but still we possibly will lack the high resolution in hotter channels. And I think that can be a future goal with the advent of MUSE and Solar Sea missions. When they will be launched, then we can better target these questions in hotter passbands along with IRIS and ground-based observatories. But specifically, if there are some experts with the SPICE, possibly Arpit can himself say about, like, if SPICE has some comparable resolution with HRI UV or not.
Yeah. Am I audible right now?
Yes.
Yes.
Yeah. Hi, Nancy. Yeah, as you have rightly pointed out that spies have a coarser resolution. That's the problem. So,
Mhm.
I cannot. I mean, I believe that spies would not be so useful in going to those in investigating those scales. So we may need some high resolution spectroscopic observation from MUSE maybe, or spice or solar sea, as you suggested. Yeah, so we need some future observation from future instruments. So that's the problem here.
Yes, and that's also my viewpoint as well.
Okay. Thank you very
Thanks.
much, Nancy.
Thanks everyone for asking such good questions, and also the questions were in form of inputs to improve the studies.
Thank you very much. So there are questions for Bablu as well. One of them is answered. So do your observations suggest any predictive patterns for the occurrence or evolution of long-lived SSTs?
I mean, for this observation, we see like downflow is quite evolving. So initially, like it is in the more downflow in the penumbra region. Then it's coming back to in umbra region, the downflow is getting stronger and stronger. So it's kind of linked to this coronal loop evolution. So the loop is changing with according. Coronal loop is changing as well as like this downflow morphology is changing. So
Okay. So another question is, given the combination of iris spectroscopy and AI imaging, what further multi-instrument observation would help confirm the mechanisms behind SSD splitting?
So this splitting we are trying to check if there is any magnetic component is changing or not, like it's connected to magnetic topology or not. So that thing we explore with this HMI thing. So we don't have like the downflow is happening around like splitting is happening around 2009, but we don't have like corresponding HMI vector magnetogram. So we took like nearby observation, and from there we see like there is like something change in magnetic topology. So from that basis we are confirming that because of most probably because of reconnection the splitting is happening.
Okay, yes, thank you very much. There is a question for Rohan. How do your findings help improve our understanding of the role of polar regions in solar activity and solar cycle?
So this the polar microwave brightenings I was talking about, they are connected to the kilogauss patches in the polar regions, and also that are connected to this plume structures. So overall, this creates like this forms the polar regions of the sun. So studying the microwave polar brightness will give us a exposure to the study of plumes and like the how this long term in long term these plumes and this small scale CVPs can contribute to the polar regions and thereby to the solar winds and all, because these plumes and nearby coronal holes are source regions of the solar wind. So there has been multiple studies previously also which tried to correlate this microwave polar brightenings with the solar winds.
Okay, thank you very much, Rohan. There are questions for Isha. Are there limitations in current simulations of spicules that need to be addressed in future studies? Is Isha around?
Sargam, I don't see her around. Maybe we can move ahead.
Okay, yeah, sure, no problem. So there are a few questions for Sandeep as well. Your findings suggest little impact on transition region or corona. How does this shape our understanding of energy transport in solar pores?
Yes, can you hear me?
Yes.
Okay, so if you see the flashes in a sunspot, which are big magnetic structures, magnetically they are strong. In terms of velocity scales, also they are much more powerful. These flashes are, I mean, they show up in the transition region in sunspots at least. But if you kind of scale down the magnetic scale of the host structure, which is a solar pore, or maybe in isolated structures like maybe network field, which is of the kilogauss scale, you do see these isolated shock events happening there also. So I think my understanding overall is that the appearance and I mean the physical mechanism and the dynamics associated with the shock should be independent of the scale, but the energetics that it carries would depend on the host structure. So the flashes appearing in the pore, maybe it is not showing up in the transition region simply because the shock happens and the energy carried out by the wave that is basically steepening is getting radiated in the chromosphere before explicitly showing in the transition region itself. So in short, I think I don't know, it's a bit complicated question. Okay, but yeah, the host structure should have an effect on the shock manifestation in different channels. So why it is not showing up explicitly in the transition region in a pore may be related to the host magnetic structure itself, which is a pore which is much smaller.
Okay, yes.
So yeah, I
Thank you,
mean
Sandeep.
that's the best answer I can give.
Yes, thank you very much. So there are some general questions in the chat. So so these are the questions for everybody, like not only for the speakers but for the audience as well. Anyone can answer this or you know comment on it. So what challenges exist in linking photospheric magnetic field evolution to chromospheric or coronal heating? So any insights
Maybe I
from,
can,
yeah, sure.
maybe I can briefly answer it because I've worked a little bit on the coupling.
Okay.
So, I mean, see, chromospheric heating is something which is very involved. So you have waves that are hitting the chromosphere, you have reconnection, you have braiding, you have n number of things that are hitting the chromosphere. Now, the physical mechanism that is dominant would depend very much on the magnetic structure you are looking at. So if you are in the quiet sun, there are a number of papers that claim that the wave heating mechanism is the dominant one. But if you start moving to a magnetically complex region, the physical mechanism that is hitting the chromosphere is much more involved. So magnetic field has a direct implication. If you start complicating the photospheric magnetic field, both strength-wise and orientation-wise, it will have a direct implication on the chromospheric heating. How does it play role? It's something that is not well understood in the community. People are still trying to work on different mechanisms. They're trying to constrain what amount of uh, acoustic heating is there, what amount of heating due to reconnection is there, what amount of, I mean, there are a number of things. So in short, magnetic field has a role, but what fraction does it play? It depends very much on the geometry of the event you're looking at.
Okay, yes. Thank you, Sandeep. Anyone would like to comment or answer this question?
Yeah, so here I would like to add that
Yes.
photospheric magnetic field and then these are very different layers of atmosphere. Photosphere behaves very differently than chromosphere, and obviously as Sandeep was saying, and which behaves very differently than corona. And if you just see the observations, the dynamics change very quickly. So the photospheric magnetic field can be a trigger, just a trigger for different events, different type of events happening in higher layers of the atmosphere. So it is difficult to have a one-to-one correspondence like this specific, for example, this specific flux cancellation is either directly related to some reconnection or some wave in upper atmosphere, or there are some multiple processes happening in between. So this will be my say, like in terms of the challenges, like how, at least from the observations, it's difficult to have a direct link.
Okay, yes. Thank you, Nancy. So I will take one more question. This is the last question for this session. So do you see any potential in using automated techniques or machine learning techniques to identify these recurring events like flux cancellation sites? If Nancy, if you have any.
Yes, yeah, sure. This is a nice input. I'm not sure who gave this, like in the chat. But yeah, definitely a nice input to use some kind of machine learning techniques. I'm not expert with machine learning, but I am aware of some of the paper in these terms by Henrik Eklund et al. Uh, yeah, so it will be interesting to see. But again, the photospheric magnetic field evolves very quickly or in a different way as the chromospheric or coronal response. So then again, I always feel that you always need a in between human intervention, like because a computer, what a code sees just the pixels, and they will not be the same event in photosphere, which is triggering some event in corona. They may not be at the same exact pixel locations. They can be slightly shifted because of the dynamics in between. So I would say yes, some semi-automated machine learning techniques, which the output of machine learning should be then intervened by a human scientist, and then
Yes.
some conclusions can be made.
Okay, thank you, Nancy. Anyone would like to comment on this?
Yeah, but if somebody who raised this question, if he or she is aware of some machine learning techniques in this aspect, then please let me know.
So, yes. So that brings us to the end of this session. I would like to thank all the speakers for their excellent presentation and all of you for joining and participating. So enjoy the rest of the conference. Thank you very much.
Yes, I would also like to thank Sargam for chairing the session, and also want to thank all the participants for participating in this the first session. And also want to remind everyone that we will again continue our conference for the day at 6 p.m. IST timing, and that will be our flash talk session. And afterwards, we will continue with the panel discussion and the invited talk. So we will see you at 6 p.m.
Thank you.
Thank you so much, everyone.